How do factories mass-produce Chupa Chups, Twizzlers, and Slush Puppy without getting the flavor all wrong? If one small step in their processes is messed up, a whole batch can be ruined instantly. In today's video, we go behind the scenes from syrup cooking to shaping and freezing systems, uncovering the unbelievable efficiency required to be at the very top of the candy industry. Hard candy only has two useful states on a lollipop line: fluid enough to be shaped and glassy enough to hold its shape. Chupa Chups style production is built to push the candy through that transition at the exact moment a stick is inserted and locked, then isolate the finished piece from humidity so it never leaves the glassy state. The most reliable way to understand the factory is to start at the forming wheel, because every upstream system exists to feed that wheel at a stable rhythm. The forming wheel is an indexed machine with cavities that open, receive a dose of hot candy, accept a stick, close to shape, then release the lollipop. Its speed is fixed by output targets, so the candy mass must arrive at the depositor at the correct temperature and viscosity, and sticks must arrive at the inserter in the correct orientation and at the correct moment. Stick handling runs continuously. Sticks are cut to length if not pre-cut, then screened to remove splinters. A deburring or air cleaning stage strips dust because dust at the interface weakens bonding and creates voids. Sticks are then singulated into individual lanes. Singulation is a mechanical sorting problem. Sticks are light and can overlap, so feeders rely on vibration, step conveyors, and guide rails to separate them. Orientation is enforced, so the same end enters the candy each time. The stick feed ends at a pick-and-place head or pusher that inserts the stick into the cavity at a fixed depth. Depth stops are mechanical, so insertion depth remains consistent even if stick length varies slightly. Depth matters because too shallow reduces pull strength, and too deep can create internal stress rings that lead to cracking. While sticks are being fed, the candy mass is being prepared as a concentrated syrup that will set into a clear glass. Sugar is stored dry and screened so clumps do not enter dissolving. Water is filtered and tempered because inlet temperature affects dissolution speed and cook stability. Glucose syrup is held in jacketed tanks so viscosity stays stable for pumping, and it functions as a crystallization control ingredient. These streams combine in a dissolver, where heat and agitation create a clear solution. The target is full dissolution with no visible grains, because undissolved grains become nucleation sites that can trigger graining later, making the candy cloudy and brittle in an unpredictable way. Concentration is performed rapidly to reach hard candy solids. In a continuous system, the clear syrup is pumped through heated coils under pressure, allowing temperature to rise quickly without boiling inside the tube. A flash chamber then reduces pressure so a portion of water instantly vaporizes and exits as steam. This flash step tightens final moisture and also reduces thermal damage because water removal occurs at a lower effective temperature than extended open boiling. Final moisture content is the main structural setting. Too much moisture yields candy that stays tacky and softens quickly. Too little moisture yields candy that becomes overly brittle and cracks at the stick interface during cooling or later handling. Immediately after concentration, the mass enters a controlled cooling section. The aim is to bring the mass to a forming temperature that is still fluid enough to be deposited and shaped, but not so hot that it degrades flavor, and not so cool that it begins to set in pipes. Heat exchangers and jacketed manifolds manage this temperature precisely. At this stage, additives are introduced because many flavors contain volatile compounds that would be stripped or damaged at peak cooking temperatures. Color is prepared as concentrated solutions or dispersions and filtered so no particles clog injectors or create specks. Flavor is metered by precision pumps into the candy stream. Injection is placed after the main heat load, so aromatics are preserved. Acid can be introduced as a solution if the recipe calls for a sharper profile, but acid timing is controlled because acid accelerates sucrose inversion at high temperature, which changes viscosity and long-term stickiness. Mixing after injection is done with static mixers or low-shear mixing manifolds that fold the flow and eliminate streaks without entraining air. Air entrapment is undesirable because bubbles create weak zones and can appear as surface pits once the candy cools. The candy mass then feeds the depositor at the forming wheel. The depositor meters a precise amount into each cavity. Portion volume directly sets lollipop size and weight. Metering is done by piston pumps or gear pumps synchronized to the wheel index. Dose accuracy matters because a low fill yields thin spots and poor stick anchoring, while an overfill creates flash that must be trimmed and increases wrapper puncture risk. The cavity receives the candy dose first or simultaneously with stick insertion depending on machine design. In one approach, the cavity is partially filled, then the stick is inserted, then a second small dose tops off and the cavity closes. In another approach, the cavity closes on a measured candy slug and the stick is driven into it. The common requirement is that candy must be plastic at the moment the stick enters, so the candy wets the stick surface and bonds as it cools. Shaping occurs when the cavity closes. The closing motion forces candy into the spherical geometry and expels trapped air. Venting channels can allow small air pockets to escape so they do not remain as bubbles. Cavity surface finish is polished, so the candy skin releases cleanly. Cavity temperature is managed so candy does not stick or smear. If cavities are too cold, the candy skin sets instantly and can trap air. If cavities are too warm, the candy remains tacky and can deform during demolding. The machine therefore maintains a stable mold temperature through internal circulation. As the formed lollipop exits the cavity, it is still hot enough that the interior is not fully glassy. It immediately enters a cooling system that locks structure. Cooling is staged. The first stage sets the outer surface quickly so the shape stops flowing. This can be done with cool, dry air directed at the candy surfaces. The second stage brings the core temperature down so the entire mass crosses into the glass state. Cooling rate must be controlled because excessive thermal gradients create stress. Stress tends to concentrate around the stick insertion zone because the stick acts as a rigid inclusion and the candy contracts around it. If the outer layer contracts much faster than the inner, microcracks can form. These cracks may be invisible initially, but can propagate during shipping or when humidity changes. Humidity control in cooling is essential. Hard candy absorbs moisture from air. If cooling air is humid, a thin moisture film can form on the warm candy surface. This film dissolves sugar at the surface and then recrystallizes as a rough haze, reducing gloss and increasing stickiness. Cooling tunnels therefore use dry air. Some lines control dew point directly, keeping dew point low enough that condensation cannot form on the candy at any point in the tunnel. Once cooled to handling temperature, lollipops are demolded or released from the forming wheel and transferred to conveyors. Transfer points are designed to avoid impact at the candy head because the surface can still mark if it is too warm. Guides support sticks rather than candy heads because contacting the head can create flat spots. The lollipops pass through inspection and rejection systems. Vision systems can detect off-center sticks, incomplete fill, surface bubbles, and flash around seams. Weight checks can detect underfill and overfill. Reject mechanisms remove defective pieces before wrapping because wrapping a defective piece wastes film and creates downstream jams. Twizzlers are manufactured by converting a cooked sweet base into a plastic, elastic candy dough, shaping that dough continuously through extrusion, setting texture through stage drying and cooling, then cutting and wrapping so the ropes stay chewy and separate without sticking. The most useful place to start is the cutter, because the cutter reveals whether the upstream dough has the right cohesion and whether the rope has been set enough to hold its geometry. If the rope tears at the cut, the dough is underhydrated or too cold. If it smears and strings, the dough is too warm or too wet. The factory therefore tunes the entire process to deliver an extrudate that behaves predictably at the knife. Upstream of the cutter, the rope travels through setting tunnels that control moisture and temperature. Those tunnels are what convert an extruded ribbon into a stable Twizzlers rope with a uniform chew. The rope exits the die warm and pliable, and its interior still contains enough water to make it sticky if packaged immediately. The setting tunnel removes a measured amount of moisture while allowing the matrix to equilibrate so the surface becomes dry enough to handle, yet the core remains chewy. Air temperature, humidity, and velocity are balanced to avoid case hardening. Case hardening creates a tough outer shell and a soft interior, which leads to cracking during bending and an uneven bite. Staged zones, warmer early zones, and gentler later zones reduce that risk. Before the rope ever reaches those tunnels, the line creates the candy dough in a cooker and mixer system designed for high solids. Sugar and glucose syrup are staged as the main carbohydrate system. Granulated sugar is screened to remove clumps and dust, because clumps dissolve unevenly and dust can scorch at hot surfaces. Glucose syrup is held in jacketed tanks so viscosity stays stable for metering. Water is filtered and tempered because inlet temperature shifts dissolution and cook stability. Starch and other structure-building solids are held dry and fed accurately because their hydration rate determines dough firmness later. Cooking starts in a dissolver where sugar is hydrated into a clear solution. That solution then moves to a cooker where heat drives off water and raises solids. The cook endpoint is selected so the base becomes plastic when cooled, not glassy like hard candy, and not fluid like syrup. The endpoint is typically controlled by temperature and by flow resistance in the cooker. If the base is undercooked, it carries too much water and produces a sticky rope that never sets. If overcooked, it becomes too stiff, causing high extruder pressure and surface cracking at the die. After cooking, the hot base is cooled into a window where powders can be incorporated without clumping, and flavors can be added without being stripped. At this stage, the line transitions from a boiling syrup process to a dough-making process. Structure formers, like starches, must be dispersed and hydrated evenly. Dry starch added directly to hot syrup would form lumps with dry cores. To avoid that, starch can be fed through high shear mixers or introduced as a slurry that is hydrated and cooked separately before blending. The goal is a continuous matrix where starch and sugars form a cohesive network. Acids and salt are staged as low-rate additions. Acid influences flavor and also changes the behavior of the carbohydrate matrix over time by shifting inversion and hygroscopicity. For that reason, acids are added after the hottest zones and mixed thoroughly but gently. Flavor and color are also added late. Flavor injection is done downstream of intense heat to preserve volatile components. Color is metered as a concentrated solution to avoid adding excess water. Once all components are combined, the mass enters intensive mixing. This is where it becomes a uniform plastic dough. The mixer uses high torque elements that fold and shear. Shear must be sufficient to eliminate streaks and fully wet powders. Shear must not be so aggressive that it whips air into the dough, because trapped air causes bubbles and weak spots in the extruded rope. Mixing endpoint is judged by uniform color, uniform torque, and a stable temperature. Temperature is monitored continuously because the dough must remain plastic but not overly soft. The dough then enters a conditioning stage before extrusion. Conditioning equalizes moisture throughout the mass and stabilizes temperature so extrusion pressure does not pulse. This can be done in a holding hopper with gentle agitation or in a screw conveyor that provides a fixed residence time. The objective is to deliver the extruder a steady feed that produces a steady rope diameter. Extrusion is the primary shaping method. The dough is fed into a screw extruder whose barrel is temperature controlled. The screw compresses and pushes the dough forward. Compression removes minor voids and increases cohesion. Barrel temperature keeps the dough in the plastic range. If the barrel is too cool, pressure rises and the rope surface becomes rough. If too warm, the rope surface becomes tacky and can collapse after exiting the die. The die defines rope, cross-section. Twizzlers ropes are typically round or slightly shaped, depending on the product format. Die temperature is controlled because cold dies cause surface tearing and hot dies cause smear. Pressure at the die is monitored. It acts as an indicator of dough viscosity and hydration. Stable pressure produces stable diameter, which matters because diameter controls final chew and package weight. Immediately after extrusion, the rope is guided by takeoff belts. Belt speed must match extruder output to avoid stretching. Stretching thins the rope and aligns the matrix, which can make the bite tougher and can produce uneven twist definition. The rope is supported so it does not sag, because sag introduces diameter variation and can cause twists to tighten unevenly. Twist formation, when used, is produced by controlled rotation relative to forward motion. A twisting head grips the rope or imparts rotation while the takeoff belt pulls. The twist pitch is set by the ratio of rotational speed to linear speed. A tighter pitch yields a more pronounced twist and slightly denser bite. A looser pitch yields a smoother rope and a softer feel. Twist must be consistent along the rope because variation creates weak points where the rope can split during cutting or packaging. After twisting, the rope enters the staged drying and cooling tunnels described at the beginning. These tunnels are engineered to hit a final moisture endpoint that supports chew without stickiness. Early tunnel zones focus on removing surface moisture so the rope can be handled without clumping. Later zones allow moisture to migrate from the core to the surface gradually and leave the rope at a stable water activity. Airflow is controlled to avoid whipping ropes into each other, and the rope is kept separated by lane guides. Once the rope reaches the target set, it passes to cutting. Cutting uses rotary blades, or guillotine cutters, synchronized to belt speed. Synchronization controls piece length and therefore piece weight. Blade sharpness is managed because a dull blade drags and creates strings at the ends. Stringing is a sign that the rope is still too warm or too wet. A clean cut indicates the surface has set and the interior has enough cohesion to fracture neatly at the blade. Cut pieces then go through a short post-set stage. This allows freshly cut ends to dry slightly so pieces do not stick end to end. It also allows any residual heat from cutting friction to dissipate. If a light surface treatment is used to improve flow, it is applied here. A tiny amount of neutral oil can be misted while pieces tumble gently. The oil film reduces surface friction and helps prevent sticking in the wrapper. Oil application is minimal because excess oil changes mouthfeel and attracts dust. Screening can follow to remove fragments created during cutting and conveying. Removing fragments improves pack appearance and reduces dust that can interfere with seals. Metal detection or other final integrity checks can be positioned here because product flow is stable and pieces are separated. Wrapping begins with controlled feeding into flow wrappers. Pieces are aligned into lanes and spaced, so each wrapper cycle receives one piece. Film is formed around the rope and sealed with heat and pressure. Seal dwell and temperature are tuned, so seals are strong without overheating the candy surface, because overheating can soften the rope and deform it under film tension. Film tension is controlled so it sits snug without squeezing the rope flat. Slush. Puppy-style slush is manufactured by producing a shelf-stable flavored concentrate, then engineering a dispensing system that freezes a diluted beverage into a suspension of tiny ice crystals without forming a solid block, then keeping those crystals moving so the product stays scoopable and uniform in a cup. The easiest way to understand the production chain is to start at the point of consumption, the slush machine. A slush machine is essentially a controlled, scraped surface freezer that must keep a mixture right at its freezing curve. It needs enough sugar and solutes to depress the freezing point, enough viscosity to keep ice crystals suspended, and enough agitation to prevent large crystals from growing. Everything that happens in the factory is designed to make a concentrate that, when diluted, behaves correctly inside that machine. The slush machine relies on a mix ratio that is tightly defined. The concentrate is not used full strength. It is diluted with water to a target sugar concentration. If the mix is too weak, freezing point rises and the machine produces a hard ice mass or large crystals that separate into watery and icy zones. If the mix is too strong, freezing point drops too far and the machine struggles to freeze enough, yielding a cold syrup rather than slush. That is why the factory builds the concentrate with a known soluble solids level and a known acidity, and why it specifies a dilution ratio. Concentrate manufacturing begins with water handling and sweetener preparation. Water is filtered to remove suspended solids because solids can seed haze and clog dosing valves. The main sweetener can be sugar syrup, glucose syrup, or a blend. For sugar-based concentrates, granulated sugar is dissolved in heated tanks with agitation until the solution becomes clear. Density is monitored because it defines sweetness and freezing behavior after dilution. For syrup-based sweeteners, the syrup is held warm so viscosity is stable, and metering is accurate. Acidity is set next because pH affects flavor perception and stability. Acid is prepared as a liquid solution for accurate dosing and then injected into the blending tank. pH is measured and adjusted to a narrow set point. A stable pH also helps preserve certain flavor components. Color is handled as a separate dosing stream. It is stored in tanks with gentle mixing and filtered before dosing so it remains uniform. Flavor is prepared as a concentrate that can be dispersed reliably in water. Many slush flavors contain both water-soluble aroma components and oil-based notes. Oil-based components are emulsified so they do not separate in the finished concentrate. Emulsification is done with high shear mixers that reduce droplet size. Droplet size matters because large droplets separate and ring at the surface, while small droplets remain stable and deliver consistent aroma. The finished flavor concentrate is filtered to remove particulate and then metered into the main blending tank. Viscosity modifiers can be included in small amounts to influence mouthfeel and crystal suspension. These components must be fully hydrated and dispersed, so they are added under controlled shear and allowed to mix until uniform. The goal is not a thick beverage, but a mix that can hold microcrystals evenly during dispensing and drinking. Once sweetener, acid, color, flavor, and any stabilizers are in the blending tank, the concentrate is mixed to uniformity without entraining air. Air entrainment can cause foaming in packaging and can affect how the concentrate mixes with water later. The concentrate is then filtered to remove any remaining undissolved particles that could settle or clog dispensing systems at retail. Quality checks on the concentrate focus on soluble solids, pH, color density, and flavor strength. Soluble solids are measured to ensure the dilution ratio will yield the intended freezing point depression. pH is checked for consistency because it affects taste and stability. Color is checked because it must remain stable in storage and consistent from batch to batch. The concentrate then moves to packaging. Packaging is designed for high sugar liquids. Concentrate is filled into jugs, bottles, or bag-in-box systems. Bag-in-box is common because it minimizes oxygen exposure and allows easy dispensing at retail. Filling uses metered valves and is controlled to avoid splashing and foaming. Caps or fitments are applied immediately. Seals are checked because leaks allow contamination and sugar crystallization around closures. Finished packages are coated and cased. At retail, the concentrate is mixed with water to the specified ratio. That mixing can be done in a separate tank or directly in the machine reservoir. The purpose is to produce a ready mix with the correct sugar concentration and acidity. The water used at retail can vary. So many systems specify filtration and cold water use to reduce variability. Inside the slush machine, freezing is achieved by a refrigerated cylinder and a rotating scraper. The cylinder wall is cooled below the freezing point of the mix. A thin layer of ice forms on the cold wall. The scraper continuously removes that ice layer and breaks it into small crystals that are pushed into the bulk liquid. Continuous scraping prevents the ice from building into a solid sheet that would block heat transfer. The rotating mechanism also keeps the entire mixture moving so ice crystals remain suspended rather than settling. The formation of microcrystals is controlled by the freezing point depression of the mix. Sugar and dissolved solids lower the freezing point so the mixture does not freeze solid at typical machine temperatures. Instead, a fraction of the water freezes as ice, while the remaining liquid becomes more concentrated. This concentrated liquid phase acts as a lubricating syrup between ice crystals. The machine aims for a steady balance where ice fraction stays in a target range. Agitation speed is a key control. If agitation is too slow, ice crystals grow larger and the product becomes coarse and icy. If agitation is too fast, the mixture can incorporate air and become foamy, and frictional heat can reduce freezing efficiency. The scraper geometry and clearance are engineered to remove ice efficiently without creating excessive shear that would heat the mixture. The machine also relies on viscosity to prevent separation. If the liquid phase is too thin, ice crystals can settle and form a dense, icy bottom layer, while the top becomes watery. A slightly more viscous liquid phase helps keep crystals evenly distributed. This is why concentrates often include small amounts of stabilizer and why the soluble solids level is strictly maintained. Temperature control in the machine is staged through a thermostat system that cycles refrigeration. The goal is not a constant deep freeze, but a controlled temperature near the mix's freezing curve. If the machine overcools, ice fraction rises too high, and the product becomes stiff and difficult to dispense. If it undercools, ice fraction drops, and the product becomes slushy syrup. Machines often use sensors that monitor torque on the agitator as an indirect measure of slush stiffness, adjusting cooling accordingly. From a factory perspective, this machine behavior drives the formulation targets. The concentrate must produce a ready mix with a predictable freezing curve. That means controlling sugar type and concentration. Different sugars and syrups depress freezing point differently and change viscosity. The factory chooses a sweetener system that creates the desired crystal fraction at typical machine temperatures. Acidity and flavor intensity are also tuned with the machine in mind. Cold temperatures reduce flavor perception. Therefore, the ready mix is formulated with enough flavor concentration to remain noticeable when frozen. Acidity can provide brightness that cuts through cold dullness. However, acidity also affects the stability of certain emulsions and can influence syrup behavior over time. The factory balances these factors. Color stability is another practical requirement. Slush is displayed in clear machine bowls and must remain visually uniform. Colorants must remain stable under light exposure and cold temperatures. The factory filters concentrate to remove particles that would settle and create gradient bands. The process for Haribo gummy bears starts in the dissolving room, where glucose syrup and granulated sugar are pumped and conveyed into a heated stainless steel vessel. This vessel, fitted with high-speed agitators and a triple-wall steam jacket, maintains constant agitation while heating the syrup mixture to around 110 degree cup walks. The goal is to dissolve the sugar completely and create a smooth, viscous base. Flow meters and density sensors monitor the syrup's solids content and concentration in real time. Once dissolved, the hot sugar solution is pumped into a vacuum cooking chamber. Here, under reduced pressure, the solution is further concentrated and residual moisture is removed. The vacuum environment allows water to evaporate at lower temperatures, preserving the integrity of thermally sensitive ingredients like flavorings and gelatin to be added later. The cooked syrup exits the vacuum chamber at a high Brix level, typically 78 or 80% solids. Gelatin, a key component of gummy bear texture, is processed separately. It is first weighed and hydrated in a pre-mixing tank, where it soaks in cold water under gentle agitation for several hours. This allows the gelatin to swell and dissolve fully. Once hydrated, the gelatin slurry is gently warmed to 60-70 degrees Celsius and held in a circulation loop to maintain its viscosity and flow properties. Agitation is constant but low shear, preserving the molecular structure essential for the signature gummy chew. The concentrated sugar glucose syrup and the liquefied gelatin are metered into a dynamic mixing vessel. In this unit, the two streams are blended under vacuum to prevent air bubbles. Inline emulsifiers introduce fruit juice concentrates, plant-based colorants, citric or malic acid, and flavor oils. These are injected at precise intervals using servo-controlled diaphragm pumps. Optical clarity, pH, viscosity, and temperature are continuously monitored and regulated. The entire mixture forms a uniform candy mass with a temperature between 75 degrees Celsius and 85 degrees Celsius. To create multiple flavor variants, the unified base is split into smaller batches and pumped into separate flavor ash color blending tanks. Each tank is dosed with its assigned fruit flavor and colorant: strawberry, lemon, orange, raspberry, apple, pineapple, each controlled by automated recipe software. Once blended, each colored candy mass is held in jacketed kettles that maintain temperature and prevent settling. The molded shaping process begins with starch preparation. Cornstarch trays, shallow wooden or plastic frames filled with fine cornstarch, are first leveled and dried. These trays pass under a starch molding board fitted with multiple metal stampers shaped like gummy bears. The stampers press into the starch, leaving behind thousands of negative impressions. The flavored candy mass is deposited into these starch impressions by a multi-head depositor. This machine uses pneumatic or servo-driven nozzles to fill each cavity with a precise volume of hot liquid candy. Each nozzle is temperature controlled to maintain candy flow without crystallization or gelation. The depositor can move in synchronized XY motion, matching the layout of cavities in the starch bed. Depositing speed exceeds several hundred rows per minute. Once filled, the trays are conveyed into a controlled environment curing room. Here, over a period of 24 to 72 hours, the gummy candy sets and matures. During this time, the gelatin network fully develops, moisture migrates, and the candy reaches its final elasticity. Room conditions are tightly regulated, typically at 20 to 25 degrees with 15 to 25% relative humidity. Airflow is carefully balanced to avoid uneven drying, and trays are rotated periodically. After curing, the gummy bears are removed from the starch using a tray inversion system. Trays are flipped onto a vibrating sieve table, and the bears fall free from the starch. Remaining starch is separated via vibration and aspiration, and returned to the starch storage system for drying and reuse. The gummy bears are now fully formed, but covered in a thin layer of starch dust. The bears enter the cleaning stage. First, they are conveyed through a rotary drum fitted with soft brushes and low-pressure air jets to remove starch residue. Next, they are transferred into an oiler drum. Here, the gummies tumble slowly while being misted with a thin layer of food-grade oil, such as carnauba wax or mineral oil. This coating gives them their glossy appearance, prevents sticking, and enhances mouthfeel. Rotation speed and spray intensity are precisely regulated to ensure uniform coverage. Polished gummy bears exit the oiler and are conveyed into an optical sorting system. High-resolution cameras scan each piece for size, shape, and surface defects. Bears that are deformed, broken, or discolored are identified by the vision system and removed by high-speed air nozzles. Approved pieces continue to the packaging line. Packaging is determined by product format: stand-up pouches, pillow bags, tubes, or bulk boxes. The cleaned gummy bears are weighed or counted using multi-head weighers that drop exact quantities into form-fill seal machines. These machines unwind printed plastic film, form it into bags, fill the bags with candy, and seal the top and bottom using heat-sealing jaws. Bag weights are controlled within +1 gram tolerance. Excess weight is trimmed in real time by the Wayfiller interface. Each package receives a date code, lot number, and barcode through an inkjet or laser coder. Vision systems verify the print quality, placement, and code accuracy. Improperly coded bags are automatically rejected. Finished bags are grouped by format and quantity and sent to secondary packaging. Secondary packaging uses automatic case erectors to form cardboard boxes. Robots or pneumatic arms load bags into the cases according to a stacking algorithm. Once filled, cases are sealed with hot melt glue or tape and printed with case-level traceability information. At the palletizing station, cases are stacked in predetermined patterns by robotic arms equipped with suction pads or mechanical grippers. Slip sheets are inserted to stabilize each layer. Full pallets are stretch-wrapped with tension-regulated plastic film and labeled with shipping data, including batch codes and destination tags. All stages of production are governed by programmable logic controllers. Each machine, from dissolver to depositor, oiler to packer, communicates with the central control system through industrial Ethernet. SCADA systems display real-time data, including syrup concentration, starch temperature, mold fill rate, curing status, polishing speed, and packaging counts. Environmental controls are maintained throughout. In the curing room, air handling systems monitor and adjust temperature and humidity minute by minute. In the packaging area, overpressure systems keep air clean and filtered. In mixing rooms, positive pressure and stainless steel surfaces ensure hygiene. Every equipment contact surface is food grade and cleaned using clean-in-place cycles or automated CIP skids. Hot detergent and sanitizing solution are circulated through tanks, pumps, and pipes on a scheduled cycle, verified by conductivity sensors and time logging. Ingredient traceability is enforced by barcode and RFID scanning at every stage. From glucose syrup intake to final packaging, every lot is digitally recorded and linked to each production batch. Quality control samples are pulled at each phase: post-mixing, post-curing, post-cleaning, and post-packaging, and tested for texture, color, pH, bricks, weight, and shelf life. Multi-flavor mixing is also supported. After curing, differently flavored gummy bears can be blended in programmable mixing drums. Servo-controlled gates release predetermined quantities of each variant, and slow tumbling ensures uniform distribution in every final package. Jolly Rancher hard candies are manufactured through a continuous high-temperature process that transforms raw materials into smooth, glossy, and intensely flavored glass-like confections. The production begins with the bulk handling of the base ingredients: granulated sugar, liquid glucose syrup, water, malic acid, flavor oils, colorants, and stabilizers. These ingredients are delivered in bulk. Sugar in silo-fed dry transfer systems, glucose syrup in heated stainless steel tanks, and flavoring compounds in sealed drums. Each ingredient is stored under controlled conditions and introduced to the production line via automated PLC-controlled dosing systems. The process starts in the dissolving station. Granulated sugar is conveyed from silos through screw feeders into a large capacity dissolving vessel. Simultaneously, liquid glucose syrup is pumped from its storage tank into the same vessel. Water is added to reach the appropriate liquid content. High torque agitators mix the ingredients as the vessel heats, typically reaching 110 degrees Celsius. The sugar fully dissolves in the syrup, forming a thick, translucent solution. The resulting sugar-glucose solution is pumped into a high-efficiency vacuum cooker. This critical piece of equipment raises the temperature while lowering the pressure, allowing the mixture to be cooked to extremely high solids content without excessive caramelization. The syrup is boiled under vacuum to between 150 degrees Celsius and 160 degrees Celsius, reaching a final moisture content below 2%. The end product is a highly viscous, super concentrated candy mass nearing the hard crack stage on the sugar thermometer. Temperature and moisture levels are controlled by inline probes. As the candy mass reaches final cooking point, it exits the vacuum chamber under pressure and moves into a cooling and mixing table. This table is heated from below and cooled from above to bring the temperature of the mass down to approximately 120 degrees. Hot enough to remain pliable, but cool enough to allow incorporation of heat-sensitive ingredients. While the mass is still semi-fluid, malic acid, flavoring oils, and food-grade colorants are injected through precise metering pumps. These ingredients are introduced through static mixers built into the cooling table, ensuring even distribution. Each flavor variant, such as watermelon, green apple, cherry, blue raspberry, or grape, is handled in a dedicated mixing zone to prevent cross-contamination. The candy mass takes on its final color, aroma, and acidic intensity at this stage. After blending, the flavored candy mass is fed into a batch, former or continuous rope former. Inside this system, the mass is compressed and shaped into a thick rope using counter-rotating rollers. The rope is then pulled through a sizing system that gradually narrows and elongates it to a uniform diameter. Servo-controlled rollers and feedback sensors maintain consistent tension, ensuring that the candy rope holds steady dimensions along its length. As the rope advances, it enters a rotary forming die. This machine uses synchronized cavities on two rotating drums to cut and shape the candy rope into individual pieces. Each cavity matches the intended candy shape, a rectangular tablet with beveled edges in the case of Jolly Ranchers. As the rope is fed between the dies, individual pieces are sheared off and simultaneously molded into their final form. The forming process is extremely fast, with cycle rates exceeding several hundred pieces per minute per line. Formed candies fall directly onto a moving belt, which carries them through a cooling tunnel. The tunnel is divided into zones with gradually decreasing temperatures, typically from 25 degrees C to 10 degrees C. Chilled, filtered air circulates above and below the conveyor. This controlled cooling ensures that the candy sets uniformly without developing sugar bloom, cracks, or warping. The candy surface hardens into a glossy, non-sticky shell with a glass-like texture. After cooling, the candies are conveyed to the wrapping station. A high-speed flow wrapper aligns the pieces single file using vibrating rails and timing screws. Each candy is fed onto a roll of waxed or metallized film printed with branding and product details. As the candy moves forward, the film is folded around it and sealed longitudinally with a heated crimping wheel. The ends are simultaneously twisted or heat sealed, depending on wrap format. Wrapping speeds often exceed 1,000 candies per minute per line. A vision system checks each wrapped candy for seal integrity, print registration, and size conformity. Cameras detect misaligned seals, unwrapped pieces, or malformed shapes. These are automatically removed from the belt using pneumatic ejectors. Approved candies continue downstream to the bulk collection point. Wrapped candies are collected and conveyed into multi-head weighers or piece-counting systems for final packaging. For bagged formats, vertical form-fill seal machines form pouches from roll stock film, fill them with the target weight or count of candies, and seal them with heated jaws. The top and bottom seals are crimped, and a tier notch or zipper may be added depending on format. Inkjet coders print date codes and batch numbers on each bag. For assorted packs, mixing drums or belt combiners randomize candies from multiple flavor lines. Servo-controlled gates release each flavor in programmed ratios. Blending is continuous, monitored by optical sensors that track color distribution across a moving belt. After primary packaging, bags are grouped into cartons. Carton erectors form boxes from flat blanks, apply glue or tape, and receive packs via robotic pick-and-place systems. The boxes are sealed, date-coded, and labeled with product information. Each box is checked for completeness using weight sensors or barcode scanning. Cartons move to the palletizing station. Robotic arms stack cartons in interlocking patterns onto wooden or plastic pallets. Slip sheets are inserted automatically between layers to improve load stability. Once the pallet is complete, it is transferred to a stretch wrapping station. A rotating arm applies stretch film tightly around the stack. A label printer applicator places barcoded shipping labels on two adjacent pallet faces. Each major system, dissolvers, vacuum cookers, batch formers, rope sizers, rotary molders, cooling tunnels, wrappers, weighers, and case packers, is governed by programmable logic controllers. The PLC network is linked to a central SCADA system, which visualizes process parameters in real time. Operators monitor syrup concentration, cooking temperature, rope speed, forming pressure, wrapping rate, and line efficiency from control stations positioned throughout the plant. Ingredient traceability is built into the software. Every raw material lot is scanned upon arrival, stored in the ERP system, and assigned to a batch number. As the batch flows through cooking, forming, and wrapping, each step is logged automatically. Final products are traceable by barcode to their raw material sources and production parameters. Clean in-place systems run automatically at the end of each shift. The dissolvers, pumps, piping, and mixing tables are flushed with hot alkaline solution, followed by clean water rinses and sanitizing cycles. Cooling belts are brushed and vacuumed. Forming dies are disassembled, cleaned manually with food-grade solvents, and reinstalled using quick clamp mechanisms. The entire factory is divided into controlled zones: raw handling, cooking, forming, packaging, and palletizing. Positive air pressure is maintained in high hygiene areas. HEPA filtration systems remove particulates from circulating air. Ambient humidity and temperature are tightly regulated, as both influence candy texture and crystallization. Factory floors are sloped for drainage and sealed with epoxy for easy sanitation. Safety systems include temperature interlocks, overpressure valves, infrared burn detectors, and emergency shutoffs across all cooking and forming zones. Machines are equipped with safety guards and light curtains. Wrapping and cutting stations include trap guards and automatic stops when foreign objects are detected. High-volume candy factories operate multiple parallel lines to meet demand. Each line runs continuously, producing tens of thousands of Jolly Ranchers per hour. Combined output can exceed 1 million pieces per shift. Candy that fails inspection or is generated during startup and shutdown is collected in a reclamation bin and disposed of or recycled in non-retail applications under controlled conditions. Jolly Rancher production is a fusion of sugar chemistry, thermal control, servo-driven precision, and automated material handling. The transformation from dry sugar to glossy hard candy involves phase change, concentration, superheating, and rapid cooling, all while maintaining tight tolerance in size, shape, and texture. The candy's signature clarity and smoothness are the result of precise cooking and air-free handling. The bite resistance and slow dissolve are dictated by gelatin-free formulation, extremely low moisture, and uniform crystal inhibition. Color intensity, tartness, and flavor intensity are tightly tuned in, dosing systems calibrated to deliver fractions of a gram with every cycle. No part of the process is manual. From sugar loading to pallet stacking, each action is governed by machines, motion controllers, thermal sensors, and inline verification tools. Each Jolly Rancher is cut, formed, cooled, wrapped, inspected, and packed in exact synchrony with the line's conveyor rhythm. The process is repeatable, uninterrupted, and engineered for scale. Nerds candy production begins with granulated sugar as the core ingredient. Delivered in bulk via silo trucks, the sugar is stored in food-grade silos and transferred into the system through pneumatic conveying lines. The sugar crystals are metered using loss-in-weight feeders and introduced into the initial tumbling drum, the nucleus of the entire Nerds production process. The defining characteristic of Nerds is their irregular pebble shape and crunchy shell. This is achieved through a continuous layering process that transforms small sugar crystals into larger, asymmetrical, coated pieces. Production starts with microcrystalline sugar particles selected for their uniform size and dryness. These seed crystals are placed into a slow-rotating stainless steel coating drum. Inside, the environment is warm and dry, with dehumidified air pumped in to prevent clumping. As the drum rotates, a fine mist of sugar syrup is sprayed onto the tumbling seeds. The syrup is composed of dissolved sugar and glucose, kept at a precisely controlled temperature and viscosity. After each syrup spray, dry granulated sugar is dusted onto the seeds. The wet syrup binds the dry sugar, and centrifugal motion within the pan ensures even distribution around each particle. The syrup sugar drying cycle is repeated hundreds of times in quick succession, forming rough, uneven lumps that define the Nerd's shape. Drying occurs continuously using a stream of low humidity, temperature-controlled air directed through perforated panels under the rotating pan. The airflow evaporates moisture from the syrup, setting each new layer of sugar into a hardened outer shell. The mass increases by milligrams with each cycle. The longer a particle stays in the pan, the larger and more jagged it becomes. This tumbling and layering process continues for 45 to 60 minutes per batch. Throughout the process, real-time particle sizing is conducted using an inline imaging system. Cameras mounted above the pan capture live footage and analyze the average diameter and surface profile of the particles. Once the growing Nerds reach target size, they are automatically discharged through a slide gate at the base of the pan. The rough white sugar lumps exit into a vibratory conveyor that removes dust and separates underdeveloped pieces. Air jets blow away fines, while a mesh sieve sorts by size. Any particles below the acceptable size threshold are recycled into the seed stream for the next batch. The acceptable pieces move toward the coloring and flavoring stage. Flavoring begins with batch division. The uncolored Nerds are split into flavor groups: grape, strawberry, watermelon, cherry, lemonade, and others. Each group enters a dedicated coating pan where they are flavored and dyed. These pans operate at higher rotation speeds to encourage rapid coverage. A fine mist of ethanol-based flavoring and food-safe dye is sprayed onto the tumbling pieces. The formulation includes fruit acids for tartness, aroma oils for intensity, and synthetic or natural dyes for color. The sprayed flavor and color mixture penetrates the porous surface of the sugar nugget, resulting in bright, vibrant colors and intense taste. As the solvent evaporates, the flavor becomes locked into the outer layer. Color intensity is monitored by spectrophotometers mounted above each pan. If deviation is detected, the spray nozzles adjust dye concentration in real time to maintain consistency. Once flavored and colored, the nerds are dried and cooled using forced ambient air blown over vibrating conveyor beds. These conveyors are lined with food-safe mesh belts to allow airflow from below. The drying stage ensures that the candies are free from any surface moisture or tackiness. Target surface temperature falls to around 20 degrees to 25 degrees Celsius. The final coating step is polishing. Polished nerds exhibit a glossy, non-sticky exterior that resists clumping. Polishing pans, similar in structure to coating pans but lined with smooth, non-stick material, are used for this purpose. As the candy tumbles, a mixture of carnauba wax and food-grade glazing agents is sprayed in a fine mist. The pans rotate at medium speed, allowing the nerds to rub against each other and buff their outer surfaces. The process lasts around 10 to 15 minutes per batch. The polished candies pass through a second set of sifters and inspection belts. Optical sensors identify off-color pieces, misshapen forms, or oversized clusters. Air jets remove rejected items from the conveyor and send them to the waste stream. The remaining pieces are ready for blending and packaging. Nerds are sold in assortments, which means different flavors must be combined in accurate ratios. This is managed by a computerized batching and blending system. Each flavor is held in a vibratory feeder that releases product onto a shared conveyor belt in precise weight percentages. Real-time flow rate monitoring is conducted using load cells beneath each feeder. The combined stream of multiple flavors forms a randomized mix of colors and shapes that fills each package. Packaging is handled by vertical form-fill seal machines and custom filling stations depending on container type. For the iconic dual-chamber box, a specialized dispenser fills two parallel compartments simultaneously. Each compartment is connected to a dedicated flavor feeder, ensuring separated streams of two flavors into the same package. The box is folded from flat blanks using a rotary carton former, and hot melt glue is applied to the seams. A hinged paperboard flap is inserted as the opening mechanism. As the boxes move down the line, a laser coding system marks each with a production batch, date code, and serial trace number. A high-resolution vision system verifies the print quality and scans the surface for correct alignment and structural integrity. Any faulty boxes are removed by push-arm rejectors and sent to the quality hold station. For other formats, such as pouches, tubes, or novelty containers, nerds are portioned by either piece count or net weight using multi-head weighers. These machines use radial feeding trays and weigh buckets to measure out small portions with extreme accuracy. The weighed product is released into packaging film or preformed containers, sealed, and passed through metal detectors for safety compliance. Once packaged, the product is conveyed into case packers. Here, robotic arms pick up individual units and place them into corrugated shipping boxes according to a preset stacking pattern. Case sealers apply hot glue or tape to close the cartons, which are then labeled and conveyed to the palletizer. Automated palletizers use robotic gantries to stack cases onto wooden or plastic pallets. Each layer is placed with millimeter accuracy to maximize vertical and horizontal stability. Slip sheets are inserted as needed to prevent shifting during transit. Once the full pallet is stacked, it moves to a stretch wrapping station. A rotating arm applies tension plastic film to secure the load. A printed label with shipping information, SKU, pallet number, and barcode is applied before the pallet is routed to the warehouse. Throughout the production line, programmable logic controllers manage all operations, from syrup spray timing to coating pan rotation, flavor dosing, weight checking, and packaging synchronization. A centralized SCADA system displays real-time data on batch progress, line speed, environmental conditions, and machine health. Operators can adjust parameters through touchscreen HMIs without stopping the line. Clean-in-place systems are used for syrup lines, coating pans, and mixing tanks. At shift's end or during changeovers, hot water and cleaning detergent are circulated through the spray nozzles, pipes, and pump systems. Coating pans are wiped down, and flavoring stations are flushed with ethanol to remove residues. Inspection cameras and flavor-specific tools are verified between batches to prevent cross-contamination. Air quality is maintained by HEPA filtration, especially in the syrup spray and flavor coating zones. Airlocks separate high-precision areas from packaging zones. Temperature and humidity are maintained to within +1 degree Celsius and +3% RH throughout the production floor. All surfaces are made of stainless steel or food-grade polymer, sloped for drainage and sanitized daily. Ingredient traceability is enforced from raw sugar intake to finished package output. Each micro batch of flavoring and coloring is tagged with barcodes and scanned into the production system. Every box of Nerds can be traced back to its sugar batch, flavor addition time, pan number, and packaging line. Smarties begin with sugar, which arrives in granulated form, stored in sealed stainless steel silos. Sugar is pneumatically transferred to the batching system through enclosed pipes. A fixed quantity of sugar is weighed and transferred to a rotating pan coater, which serves as the initial forming chamber. Inside the pan coater, fine misting nozzles spray a sugar solution to bind dry sugar particles. Centrifugal force distributes the syrup across the pan surface, while rotation builds uniform cores. These rotating pans are tilted slightly forward and spin at a constant rate to ensure layering occurs evenly on all particles. Each pass adds mass to the sugar cores, which slowly grow into uniform spheres. The syrup concentration is adjusted by flow meters to maintain proper adhesion without overcoating. Once the cores reach target size, they are dried using dehumidified air blown from a ring manifold mounted inside the pan. The dried sugar cores are sieved using vibratory screens to separate non-uniform particles. Undersized or misshaped cores are removed and recycled through a remelt system. Only cores within strict diameter tolerance proceed to the coating line. The selected cores are transferred by vacuum conveyor to the color coating pans. These pans are also tilted and use internal baffles to create tumbling action. Colored sugar syrup is sprayed onto the rotating cores using precision air-assisted atomizers. Each color batch is processed separately to avoid pigment contamination. The syrup contains food-grade dye and a fixed ratio of glucose to prevent crystallization. The color builds in thin transparent layers with multiple passes. Air jets accelerate, drying between each pass without disturbing coating adhesion. A fixed weight of syrup is applied per kilogram of product to ensure consistent color intensity. Optical sensors monitor surface reflectivity to detect coating completeness. Each pan batch continues until desired hue and opacity are reached. After coloring, the coated Smarties move to a polishing stage where they are treated with a food-grade wax solution. This step is done in smaller polishing pans with a lower tilt angle and slower rotation. A fine mist of carnauba wax is sprayed using atomizing nozzles to create a thin surface layer. Polishing lasts 5 to 8 minutes, depending on batch size and wax viscosity. Final gloss level is checked using a reflectometer. Finished pieces are then cooled using ambient airflow and discharged onto an inspection conveyor. The conveyor passes beneath a digital camera array, which, checks for shape consistency and surface defects. Air jets remove any pieces outside tolerance. The remaining product enters a vibrating chute that feeds into the printing station. Each Smartie is printed with a white edible ink letter using a rotary pad printer. The printer contains a silicone pad which presses into an ink-filled cliché plate to pick up the letter. The pad then presses onto the candy surface, which conforms slightly to ensure full transfer. Ink drying occurs almost instantly due to ethanol-based solvents. The printed pieces continue on a conveyor to a temporary holding bin. The bin meters product flow into the packaging line, which includes weighing scales and filling hoppers. Weighing scales use load cells to dispense exact net weight quantities into each chute. The chutes feed either roll wrapping machines or blister forming equipment depending on format. For roll packs, Smarties are released onto a continuous wrapper film. Film feeding is driven by a servo motor, which synchronizes with the candy drop. Once the set count is reached, rotary knives cut the film into individual lengths. Heat seal bars close both ends of the film around the product. Roll packs exit the machine and are stacked in cartons. Blister packs are made by forming cavities in thermoplastic film using vacuum and heat. Smarties are dropped into each cavity by a gate dispenser. A foil lid is laminated to the top of the film using a heated roller. Boxed formats involve volumetric fillers, which drop measured product into upright cartons. Cartons are formed from flat blanks using a rotary carton erector. Filled cartons pass through a hot glue sealing station before entering the coding unit. All packaged formats are printed with batch number and timestamp using thermal inkjet printers. Finished units move along conveyors to the collating area, where robotic arms group products into larger cases. Cases are formed by an automatic case erector, which folds and seals flaps using glue. Collated products are pushed into the case and the top is sealed in a separate station. Each case is labeled using a print and apply system that adheres barcodes and contents description. Cases are transferred to palletizers, which stack them onto wooden or plastic pallets using a vacuum gripper arm. Stack height is determined by case weight and stability requirements. Full pallets are stretch wrapped with film before transfer to cold storage. Color production is kept isolated to prevent cross-contamination. Each color is made using dedicated syrup tanks and pump circuits. After each batch, the syrup lines are flushed with hot water, followed by a compressed air purge. Sugar syrup used for coating is heated in double-jacketed tanks with agitation. Temperature is maintained at 110 degrees Celsius for flow and binding properties. Syrup is filtered through a fine mesh screen before entering the coating pan spray system. Atomizing nozzles are adjusted for droplet size using air. Pressure regulators. Smaller droplets create smoother surfaces, while larger droplets increase build-up rate. The nozzle distance from product bed affects coverage radius and drying uniformity. Drying air is conditioned by passing through a desiccant dehumidifier and a preheater. Air temperature and humidity are set based on coating thickness. Flow rate is managed through adjustable louvers at the pan inlet. Pan rotation speed affects rolling frequency and layer adhesion. Faster speed increases agitation but can cause chipping. Slower speed allows better leveling of syrup layers but requires longer cycles. Optimal speed is determined for each pan size and batch load. Letter printing uses ink that contains titanium dioxide for opacity. The cliché plate is laser etched with letter shapes and mounted on a rotary drum. Each pad picks ink from the etched cavity and applies it to a passing candy unit on a timing belt. Positioning is maintained using optical encoders that sync the pad. Strike with the candy location. Missed prints are detected by contrast sensors. These pieces are removed using side air jets directed by the control unit. Packaging materials are fed from rolls mounted on unwind stations. Tension is controlled by dancer arms connected to motorized brakes. Registration marks on the film ensure cutting and sealing alignment. Heat seal jaws are PID controlled to maintain consistent seal strength. For rolls, twisted ends are formed using roller bars that compress the candy tube while rotating. The twisted sections are heat set to preserve shape. Cartons and boxes use cold form glue that is applied by nozzles onto folding flaps. Glue cure time is matched to conveyor speed and compression length. Cartons are held under pressure for 2 seconds to ensure bond strength. Filled cartons are buffered before case packing using a serpentine conveyor that absorbs flow variations. Cases are arranged in alternating layer patterns to improve stacking strength. Full pallets are weighed before wrapping to confirm case count. Throughout the Smarties production process, all mass transfer points are closed-loop systems to prevent material loss. Product handling uses gentle slopes and controlled angles to minimize breakage. Surfaces in contact with product are coated with anti-static and anti-stick layers. Production parameters are logged in real time, including syrup temperature, pan speed, air humidity, atomization pressure, print contrast, and packaging throughput. These values are compared to target set points every batch cycle. Waste product is collected at each rejection point and separated by type. Non-printed Smarties can be remelted and reused. Printed or overcoated pieces are ground and disposed of in a controlled waste stream. Jolly Rancher candies are produced by first preparing a concentrated sugar syrup, which serves as the structural base of the hard candy. Granulated sucrose is stored in silos and pneumatically transferred into batching hoppers positioned above stainless steel dissolution tanks. Liquid glucose or corn syrup is pumped from heated holding tanks and metered into the same batch tanks through insulated lines. The ratio of sucrose to glucose is fixed and varies slightly by flavor to affect hardness and glass transition behavior. Water is added last to the batch to begin dissolution. The tank uses an agitator with 3-blade impellers mounted on a vertical shaft that mixes all ingredients until fully homogenized. Tank temperature is held at 85 degrees Celsius to accelerate solubility without initiating premature boiling. Once dissolved, the sugar mixture is transferred to a continuous cooker via positive displacement pump. The cooker is a tubular heat exchanger that uses steam as a heating medium to bring the syrup to final cooking temperature. As the syrup flows through the tubes, internal temperature rises to approximately 160 degrees Celsius. This evaporates most of the water and converts the syrup into a thick, amorphous mass. The syrup exits the cooker under pressure and is fed directly into a vacuum chamber where remaining moisture is removed rapidly. Vacuum levels are controlled using a pressure regulator that lowers boiling point to minimize heat degradation. The product exiting the vacuum chamber has a moisture content of less than 2%. This highly viscous candy mass is discharged onto a stainless steel cooling table coated with a non-stick surface. A mechanical scraper arm moves the mass back and forth to reduce temperature and increase viscosity. Cooling continues until the mass reaches a pliable yet non-flowing state, typically at around 110 degrees Celsius. At this stage, acidulants such as malic acid or citric acid are added manually or through a heated dosing manifold. These acids provide the sharp fruit flavor profile typical of Jolly Ranchers. Simultaneously, concentrated flavor oils are added using a high shear mixer attached to the edge of the cooling table. Colorants are blended in at the same point and are selected to match each flavor. The flavoring and coloring step is brief because extended mixing can cause volatile loss. The candy mass is worked using mechanical paddles that fold and compress the batch until all additives are fully incorporated. This creates a uniform mass with consistent flavor distribution and visual appearance. The mass is divided into portions and transferred to a forming line using heated transfer arms. The forming line begins with a batch roller, which elongates the candy into a rope of constant diameter. The batch roller consists of 4 or 5 heated rollers that rotate in sequence and pull the candy through narrowing gaps. The temperature of each roller is individually controlled to prevent sticking. As the rope exits the final roller, it is passed through a rope sizer, which uses a die to shape the candy into an exact diameter. This diameter is based on the final desired piece weight and length. The rope is pulled forward by synchronized feed rollers, which deliver it into the die-forming machine. The die-forming machine consists of a rotating drum with recessed cavities. As the rope enters the drum, a knife presses it into the cavities and shears the candy at regular intervals. Each cavity is shaped like the final product and creates a pillowed form on the surface of each candy. Formed pieces are ejected from the die cavity using a release pin. Pieces fall onto a vibratory cooling conveyor that carries them away from the die head while further reducing internal temperature. The conveyor uses airflow and mechanical shaking to ensure the candies remain separated during cooling. Cooling continues until surface temperature falls below 40 degrees Celsius. At this point, the candy is sufficiently rigid to avoid deformation. Candies pass through an oiling drum, where a small amount of anti-stick oil is applied to prevent adhesion during storage. The candies are then conveyed to a storage bin or directly to the wrapping line depending on production sequencing. The wrapping machine used for Jolly Ranchers is typically a high-speed twist wrap unit. Formed candies are fed into a flighted conveyor that spaces them evenly before wrapping. Wrapping film is fed from a roll and cut into segments that match the length of each candy. A film grabber aligns each piece of film with the incoming candy. The machine wraps the film around the candy and twists both ends simultaneously using 2 rotating fingers. The twisted ends are pressed to retain their shape. Wrapped candies exit the machine on a discharge conveyor and are grouped automatically into rows for further handling. Each component of the line operates continuously and in coordination with upstream and downstream modules. Flavor changeovers require the flushing of flavor oil lines and cleaning of the color tanks. The cooling table surface is scraped and cleaned before introducing the next batch. Each flavor batch typically corresponds to a specific production run to avoid cross-flavor contamination. Color consistency is maintained by using pre-blended pigment dispersions added through precision pumps. These dispersions are stirred continuously in a heated jacketed tank before injection into the batch. Volume dispensed is controlled by a pulse counter that records each pump stroke. Flavor strength is managed by load cell feedback, which calculates the candy mass and adjusts flavor oil volume accordingly. The oils are kept in nitrogen blanketed tanks to reduce oxidation during storage. Rope speed through the batch roller is monitored by encoder feedback and automatically adjusts based on temperature, mass viscosity, and die pressure. A thermocouple embedded in the rope housing measures product temperature before it enters the die head. If the temperature is too low, the feed rollers reduce pull rate to prevent rope breakage. If too high, the batch roller slows to allow cooling. The forming drum speed is matched to rope speed using a gear ratio that ensures clean cuts at every cavity. Cavity pressure is balanced using pneumatic tensioners to avoid candy flash or deformation. As the knife cuts each candy, pressure sensors detect load and ensure alignment. Misformed candies are diverted by an air jet triggered by machine vision sensors that detect dimension or position errors. The vibratory cooling conveyor has a zoned design with separately controlled fans. Airflow is filtered and directed through baffles that create a laminar stream. The shaker speed varies by batch size and surface stickiness to optimize separation. Oiling quantity is regulated by metering pumps connected to a fine mist nozzle array. Only a trace amount of oil is used to avoid impacting flavor or texture. Excess oil is collected in a catch tray and recycled through an inline filter. The twist wrapping film is made of cellophane or oriented polypropylene and pre-printed with branding and flavor identifiers. Film tension is controlled by a feedback loop that adjusts brake pressure on the film unwind shaft. Knife blades that cut the wrapping film are positioned by servo motors that adjust cut length in real time based on candy dimensions. Heat sealing is not used on these wraps because the twist retention is mechanical. The wrapping process operates at up to 1,000 pieces per minute and includes redundant feeders to reduce downtime. Candy positioning is controlled by optical sensors that detect each piece and signal the film release mechanism. Throughout the Jolly Rancher process, thermal conditions are tightly regulated to maintain texture and gloss. Humidity is controlled in the cooling and forming areas to prevent surface fogging or sugar bloom. Runts are produced by compressing flavored and colored dextrose-based powders into shaped tablets using rotary forming presses. The process begins with the blending of base ingredients in large capacity ribbon mixers. Dextrose, which forms the primary bulk of the candy, is loaded from silos through vacuum transfer lines into the mixer. To this, a precise amount of maltodextrin is added using screw-driven feeders. Citric acid powder is added to enhance flavor sharpness and to balance sweetness. Calcium stearate is introduced as a lubricant to prevent sticking during compression. Microcrystalline cellulose is used to improve structural integrity and reduce friability. Each component is weighed automatically by load cell controlled bins before entry into the mixing chamber. Mixing occurs under low speed agitation for uniform distribution of fine powders. After dry blending is complete, a liquid binding solution is sprayed into the mixture. This binder typically contains invert sugar or corn syrup diluted in water to enhance adhesion during compression. Spray nozzles mounted at the top of the mixer deliver atomized binder in controlled bursts while the mixer continues rotation. The partially moistened blend exits the mixer and is transferred via auger to a fluid bed dryer. The dryer uses filtered air heated to approximately 60 degrees Celsius to remove excess moisture while preserving binder functionality. The drying process takes between 15 and 20 minutes and ends when the target moisture content of around 1.5% is reached. Once dried, the mixture is cooled to ambient temperature through a vibrating cooling conveyor fitted with perforated air plates. The cooled material is then screened using a rotating sieve to break up clumps and ensure consistent particle size before compression. Oversized particles are ground and reintroduced into the feed stream. The prepared mix is transferred to an overhead hopper, which feeds directly into rotary tablet presses. Each press consists of a die table that rotates horizontally with multiple tooling stations. As the table turns, powder falls into open dies, which are then compressed between upper and lower punches. Each die cavity is shaped according to the desired fruit design, such as banana, grape, or strawberry. The punches apply high pressure for a brief duration, which compacts the powder into a solid mass. Ejection cams raise the lower punch to release the formed candy, which is then pushed out of the die onto a discharge belt. Compression force, dwell time, and punch speed are continuously monitored by sensors on each press station. Press speed is generally between 40 and 60 rotations per minute, depending on candy size and complexity. Multiple presses run in parallel to produce different shapes and colors. Formed candies exit the press at a controlled rate and are transferred by belt to the coating drums. These drums are inclined and rotate slowly to tumble the candy pieces without damaging them. A sugar syrup is applied via a spray manifold mounted inside the drum. The syrup contains dissolved sugar, colorants, and flavor oils specific to each fruit variant. Application of the coating syrup occurs in cycles, with drying air blown between each layer. The syrup forms a smooth, glossy shell around the compressed candy core. The drying air is filtered and maintained at a temperature of 35 to 40 degrees Celsius to prevent syrup crystallization. Each coating drum batch completes between 12 and 15 cycles before final gloss is achieved. Color uniformity is monitored using inline optical sensors mounted at the drum exit. Any candy that fails color threshold is automatically diverted by air jets to a reject bin. Accepted candies continue to the polishing stage. Polishing drums are similar in design to coating drums, but operate at lower speeds. A light mist of food-grade carnauba wax is sprayed onto the tumbling candy to enhance surface shine. Polishing continues for 5 to 8 minutes until all pieces achieve uniform gloss. Polished candies exit the drum onto a vibratory conveyor, which aligns them for inspection. A camera-based sorting system checks each candy for cracks, deformities, or uncoated surfaces. Machine vision algorithms trigger solenoids to remove defective units from the flow. Correct candies pass to a final drying tunnel where low humidity air circulates to stabilize the coating. Tunnel dwell time is approximately 3 minutes. After drying, the candy enters the counting and filling station. The filling machine uses rotating discs with pockets that hold fixed numbers of candies. Each pocket empties into a vertical chute leading into packaging units. Depending on packaging format, the candy is dispensed into cardboard cartons, plastic tubes, or small bags. Film-fed vertical form-fill seal machines receive candy loads by timing screw and funnel. The machines form packaging film into tubes, seal the bottom, drop candy, and seal the top. Each package is cut and dropped onto a belt, leading to collection bins. Plastic tubes are filled by inline auger fillers that rotate open-bottom tubes beneath product chutes. A single rotation dispenses a set quantity of candy. Filled tubes are sealed with heat or snap-on caps, depending on design. Cardboard boxes are filled on a separate line using drop gate fillers. Boxes are pre-formed using a mechanical folder and pushed through filling lanes. After filling, a flap tucker folds and glues the top closed. All packaging units pass under an inkjet printer that applies batch codes and timestamps. Packages are then grouped using collating conveyors and shrink-wrapped or cased based on distribution requirements. Throughout production, each shape and flavor batch runs in dedicated equipment zones to prevent cross-contamination. Banana-shaped candies are yellow and flavored with isoamyl acetate. Strawberry-shaped candies are red and flavored with ethyl methylphenyl glycidate. Grape, lime, and orange follow similar combinations of shape, color, and ester-based flavoring. Each flavor's syrup is prepared in separate jacketed tanks to preserve aromatic quality. Syrup concentration is adjusted to match coating viscosity for that flavor's specific sugar crystal structure. Color pigments are pre-blended in glycerin or propylene glycol and introduced during syrup preparation. The compressed candy core has a fixed porosity that allows coating to adhere without absorption. Compression tooling is polished and coated with anti-stick materials to maintain shape definition and reduce mechanical drag. Die cleaning is performed at regular intervals using brush systems that rotate within the die cavity. Punch alignment is verified using a laser sensor that checks deviation in vertical axis during operation. Air supply for fluid bed drying, cooling, and coating is sourced from a centralized HVAC unit with HEPA filtration. Ducting routes temperature and humidity-controlled air to each stage through pressure-controlled dampers. All rotary presses, coating drums, and polishing machines are synchronized via a central PLC that tracks product flow and batch progression. Any variance in throughput or processing time automatically adjusts downstream processes to maintain balanced output. Candy weight is checked at the end of the forming line using a dynamic scale belt. If a candy is too light or too heavy, it is removed before coating. Moisture content of coating is measured using infrared sensors to determine residual water before drying. Compression tooling for Runts is machined from hardened stainless steel and engraved with shape detail using CNC lathes. Replacement tooling is stored in temperature-controlled drawers to prevent thermal distortion. Punch lubrication is automated with small volume silicone oil injections at each cycle. Candy density is maintained at a specific range to avoid breakage during packaging. Too much compression leads to brittle texture, while too little causes shape distortion. Process control data is logged continuously and reviewed for each shift. At no point is the candy handled manually until fully wrapped or boxed. The entire line from blending to packing operates as a continuous feed with variable speed, drives that adapt to real-time conditions. The manufacturing process of Kinder Bueno begins with the preparation of the wafer batter. The primary ingredients, wheat flour, water, vegetable oil, lecithin, and leavening agents, are fed from storage silos and tanks into a stainless steel batching system. Each component is dosed with gravimetric precision, and the batch is mixed in a jacketed high-shear mixer. The flour is delivered via screw conveyors, water is flow metered, and emulsifiers are introduced through liquid dosing pumps. Mixing time, rotation speed, and temperature are regulated to ensure that the batter reaches a uniform consistency suitable for rotary plate baking. Viscosity is continuously measured during mixing to maintain the desired flow behavior. The mixed batter is transferred to the baking system via diaphragm pumps. A rotary oven equipped with a sequence of upper and lower metal baking plates receives the batter through a synchronized volumetric depositor. The baking plates close, forming a mold that defines the half-shell structure of the wafer casing. The plates travel through the baking chamber where they are heated via direct flame or electric elements. Internal plate temperature is maintained between 160 degrees Celsius and 180 degrees Celsius, with each shell requiring approximately 90 seconds of exposure to solidify and develop structural integrity. As the mold progresses through the oven, moisture is evaporated, and a thin, crisp wafer forms along the contours of the mold cavity. Upon completion of the baking cycle, the plates open automatically. Mechanical lifters remove the wafer shells and place them onto a wire mesh conveyor. The shells are cooled using forced ambient air delivered through adjustable nozzles positioned above and below the conveyor. The shells then enter a trimming station where a high-speed rotating blade removes excess material from the shell edges to ensure uniform shape and dimension. The trimmed shells are rotated and aligned into uniform orientation using guide rails and belt positioners. The output is arranged into index stacks for timed transfer to the filling system. The hazelnut cream filling is produced on a separate line. Whole hazelnuts are delivered in bulk and transferred into a vibratory screening unit that removes any residual shell fragments or extraneous material. The screened nuts are routed through a mechanical conveyor to a continuous roasting system. Roasting is carried out in a rotating drum oven or a belt-type hot air roaster. The roasting temperature is controlled at 150 degrees Celsius to 160 degrees Celsius, with exposure times ranging from 20 to 25 minutes depending on kernel size. Roasted hazelnuts are cooled rapidly using counterflow ambient air to prevent oil migration. Blanching follows, using mechanical abrasion rollers to remove the skin. Blanched nuts are transported directly to the grinding section. Hazelnut grinding is conducted in 2 stages. The first stage uses a hammer mill or pin mill to reduce particle size to below 200 microns. The ground nut mass is then passed through a ball mill where particle size is further reduced to below 30 microns. The resulting hazelnut paste is transferred to a mixing tank equipped with counter-rotating blades. To this paste, specific quantities of refined sugar, vegetable fat, milk powder, and lecithin are added. The blend is agitated at a controlled temperature, generally between 35 degrees Celsius and 40 degrees Celsius, to produce a homogeneous, spreadable cream. Once fully emulsified, the hazelnut cream is transferred to buffer tanks maintained at a consistent temperature and mixed gently with slow-speed impellers to preserve structure. Wafer shells are filled using a precision depositor that aligns with each open wafer cavity. The hazelnut cream is pumped through heated stainless steel lines and dispensed in measured volumes through multiple nozzles. The depositor operates in cycles synchronized with the conveyor to allow for accurate deposit into each cavity. Each half shell receives a center-aligned column of cream filling, stopping short of the rim to accommodate sealing with the upper half shell. After deposition, the second wafer half is picked and placed onto the filled shell using robotic vacuum grippers. Sealing of the wafer is carried out with a dual pressure belt system that presses both halves together at controlled force. The sealed wafer unit is transferred to the next processing stage, where the internal coating is applied. A tempered chocolate mixture is circulated through a closed-loop system and delivered to the coating station. Each sealed bar passes beneath a chocolate curtain that applies a uniform internal chocolate layer around the wafer structure. An excess removal mechanism uses vibration and compressed air knives to prevent pooling or uneven distribution. The coated units then enter a cooling tunnel, which uses recirculated chilled air to bring the chocolate to a solid state without thermal shock. Tunnel dwell time is determined by belt speed and tunnel length, ensuring full crystallization of the chocolate layer. After internal cooling, bars are conveyed to the external enrobing line. This section applies the milk chocolate outer coating. The coating chocolate is prepared in advance by melting, tempering, and circulating through jacketed pipes maintained at 30 degrees Celsius to 32 degrees Celsius. The bars pass over a mesh belt conveyor under an overflow system, where chocolate is applied to the top, sides, and bottom simultaneously. The base layer is achieved through contact with a rotating chocolate-coated roller positioned beneath the belt. Excess chocolate is removed using oscillating air jets and a vibrating belt section. Once the milk chocolate layer is set, decorative stripes of dark chocolate are applied. A multi-head depositor positioned above the belt releases thin lines of dark chocolate in a controlled motion pattern, creating the characteristic curved stripe design. The application of stripes is synchronized with belt movement, and chocolate flow rate is controlled using peristaltic pumps and pressure regulators. The decorated bars are sent through a secondary cooling tunnel. This unit is divided into multiple temperature zones, gradually reducing the product temperature to ensure final structure without bloom or surface defects. After exiting the second cooling tunnel, the finished bars are individually wrapped using horizontal flow wrapping machines. Each bar is conveyed into a forming box where the wrapper film is folded around the product and sealed longitudinally by heated rollers. End seals are created using rotating sealing jaws that compress and heat seal the film ends. The temperature, jaw pressure, and dwell time are adjustable parameters based on film type and bar temperature. The wrapping material is pre-printed with branding and is fed from reels under tension-controlled rollers. Wrapped bars are grouped by rotary collectors and transferred to the bar collation unit. This unit counts bars and arranges them for packaging into twin packs or other desired formats. Grouped units are transferred into pre-formed secondary sleeves or cartons. These are closed with mechanical tucks or glue application systems, depending on the product configuration. The fully assembled and sealed cartons are discharged from the line at regular intervals. At no point during the process are the components exposed to cross-contamination, as each line is physically separated and supplied with dedicated material flow and thermal systems. The entire production line is configured to operate in continuous motion with conveyors, deposition units, coating systems, and cooling tunnels fully synchronized. All components, from batter mixing to final wrapping, are connected through an uninterrupted mechanical chain, resulting in fully assembled, filled, coated, and wrapped Kinder Bueno units. Production of Bounty begins with the formation of the coconut filling. The core ingredient, desiccated coconut, arrives in bulk and is stored in sealed silos or stainless steel containers. The coconut is unloaded via vacuum conveyors into pre-cleaning units, where it passes through a series of vibratory sieves and magnetic separators to remove oversized flakes, fine powder, and metal fragments. After initial screening, it enters holding hoppers equipped with agitation paddles to prevent bridging during downstream feeding. From the hoppers, desiccated coconut is metered into large-scale batch mixers. In parallel, a blend of glucose syrup, invert sugar, and emulsified fats is prepared. Glucose syrup is stored in heated bulk tanks and is circulated through jacketed piping systems to maintain flow at a consistent temperature between 45 degrees Celsius and 60 degrees Celsius. The syrup is pumped into dosing vessels, where flow rate is precisely controlled via mass flow meters. Invert sugar, used for moisture retention, is added next. Solid fats, typically palm kernel or coconut oil, are stored in insulated tanks, liquefied by indirect heating, and pumped through a closed-loop recirculation system to maintain fluid consistency. The syrup-fat mixture is introduced into the batch mixer with the desiccated coconut. The mixer, usually a double Z paddle or ribbon blender, operates at low to medium shear to avoid breaking the coconut structure while ensuring even distribution of binders. The mixing chamber is jacketed to maintain the blend at 40 degrees Celsius to 45 degrees Celsius, aiding uniform fat dispersion. Mixing duration is controlled by programmable logic controllers and typically runs for 8-12 minutes per batch, depending on volume. Load cells beneath the mixer verify batch mass consistency. The completed coconut mixture is discharged through a pneumatically controlled gate valve onto a spreading conveyor. This conveyor leads to a slab, former consisting of a series of compaction rollers and edge formers. The mixture is shaped into a continuous ribbon or slab of fixed width and height. A top leveling blade smooths the surface, and lateral guides maintain slab width, typically between 100 mm and 150 mm. Roller pressure and conveyor speed are adjusted to control slab density and moisture distribution. The continuous slab moves into a cooling tunnel to solidify the matrix prior to cutting. The tunnel uses chilled air circulated by variable speed blowers. Tunnel length ranges from 15 to 25 meters depending on line throughput, and internal temperature is maintained between 5 degrees Celsius and 10 degrees Celsius. Dwell time in the tunnel is approximately 3-5 minutes, enough to reduce the slab surface temperature to below 15 degrees Celsius. Exiting the cooling tunnel, the solidified slab is conveyed towards the portioning system. It first encounters a longitudinal cutting unit consisting of rotary disc blades that slice the slab into multiple parallel lanes. Blade spacing is adjustable based on final product width. These lanes proceed to the transverse cutting station equipped with servo-controlled guillotine knives. Blade actuation is synchronized with conveyor speed to ensure precise cut length, generally between 55 mm and 65 mm per piece. Each resulting rectangular coconut core is now a preform ready for enrobing. These preforms are transferred via a servo-driven indexing conveyor onto a perforated steel mesh belt leading into the enrobing section. In the enrober, the preforms pass beneath a tempered milk chocolate curtain. The chocolate, maintained at 30 degrees Celsius to 32 degrees Celsius, is pumped from a holding tank that continuously circulates it through a tempering unit. The tempering process cycles the chocolate through heating, cooling, and reheating, producing a stable beta crystal structure for gloss and snap. As the coconut bars pass beneath the chocolate curtain, they receive full top and side coverage. Simultaneously, a bottoming roller applies chocolate to the base through contact with the lower mesh belt, which has been pre-coated with a thin chocolate layer. Total chocolate deposition is regulated by overflow weirs and return flow pumps. After enrobing, the bars enter a vibrating section, which removes excess chocolate and promotes even distribution across the surface. Next, the enrobed bars pass under dual air knife systems, which blow away excess chocolate and refine the final bar shape. The air knives are positioned above and to the sides of the conveyor belt and deliver high-velocity air streams shaped by nozzles. Air pressure and flow direction are adjustable to control surface smoothing and eliminate drips or streaks. From here, the bars enter the cooling tunnel for chocolate crystallization. This tunnel is temperature zoned, typically starting at 12 degrees Celsius and gradually reducing to 6 degrees Celsius. Multiple air curtains prevent moisture intrusion. The cooling belt is constructed from food-grade plastic or stainless mesh and runs at a speed coordinated with enrobing throughput. Time inside the tunnel varies between 8 and 12 minutes, depending on bar dimensions and chocolate mass. Upon exiting the tunnel, the cooled bars are transferred via synchronized belts to the wrapping line. The wrapper feed system pulls pre-printed film rolls into a forming collar, where the film is shaped into a tube around each bar. The longitudinal seal is created by a heated roller or ultrasonic sealer. Transverse seals are applied at both ends by heated rotary jaws. The wrapping material is a multi-layer laminate typically composed of oriented polypropylene and metallized films for moisture barrier performance. The wrapping machine cuts and seals at rates exceeding 300 units per minute. Temperature, tension, and registration are electronically controlled. Eye marks on the film align the print with the bar position. Any deviation beyond +1 mm triggers automatic correction. Wrapped units are discharged via conveyor to a belt that aligns them for secondary collation. Depending on format, bars are grouped into twin packs or multi-packs. Mechanical pushers or robotic pickers load grouped units into cartons or wraparound sleeves. These cartons are formed from flat blanks fed from a magazine and folded using pneumatic actuators. Glue is applied at specific points by hot melt applicators, operating between 160 degrees Celsius and 180 degrees Celsius. Carton forming and glue compression are synchronized with product loading to ensure square, tight packages. Each carton is then indexed onto a conveyor for further grouping if needed. Although palletizing is excluded from this explanation, the output at this point consists of individual or grouped bounty bars, fully formed, enrobed, cooled, wrapped, and mechanically packed in a continuous flow operation. The production process is continuous, with coconut mass production, slab forming, cutting, chocolate tempering, enrobing, cooling, and packaging all connected via coordinated mechanical systems. Component flow is fully synchronized. All pumps, motors, conveyor drives, cutting blades, and enrobing units are driven by variable frequency drives and controlled via programmable logic controllers. Sensor arrays track mass, temperature, flow rate, belt speed, and chocolate level at multiple points. Each mechanical action is executed with predefined parameters for precise size, mass, and texture control. At no point is there any batch handling beyond the initial coconut sugar fat mixing phase. Once the slab is formed, the process is entirely linear and uninterrupted. Chocolate is continuously tempered and recirculated. Belt tension and alignment are automatically corrected by sensors positioned at key transition zones. All rotating equipment is balanced to minimize vibration and mechanical wear during high-speed operation. The only thermal processes are the initial cooling of the coconut mass to retain structural integrity during cutting and the two-stage cooling of the enrobed bar for chocolate crystallization. These are separated and isolated to prevent temperature overlap and ensure phase separation between fat-based ingredients and sugar syrups. Production of Baby Ruth chocolate bars begins with preparation of three major internal components: nougat base, caramel layer, and roasted peanuts. Each is manufactured separately in dedicated lines before being combined, enrobed, cooled, and wrapped. Nougat preparation begins by heating a sugar syrup composed of granulated sugar, corn syrup, and water in stainless steel cooking kettles. The mixture is continuously agitated with paddle mixers while being brought to a target temperature between 115 degrees Celsius and 125 degrees Celsius. The heated syrup is transferred via jacketed piping to a whipping kettle. In parallel, a protein solution, commonly egg white solids or milk protein concentrate rehydrated with water, is prepared in a separate mixing vessel and whipped at high speed using rotary whisks to introduce air and build foam structure. The hot syrup is gradually introduced into the aerated protein foam under continuous mixing. The injection is controlled with a metering pump to regulate flow rate and avoid protein collapse. Once combined, the mixture forms a dense but aerated nougat base. Additional flavoring agents, such as vanilla or milk powder, are introduced at this point. The nougat is discharged onto a cooling table or directly onto a continuously moving belt coated with release agent. The mass is shaped into a sheet using roller levelers that compress it to a uniform height, generally between 12 mm and 18 mm. Edge guides ensure consistent width. The nougat sheet passes through a cooling tunnel with forced air at 5 degrees Celsius to 10 degrees Celsius, solidifying the mass to prepare for the caramel layer. Dwell time in the tunnel is determined by line speed and product thickness. The cooled nougat sheet exits the tunnel and proceeds to the caramel application station. Caramel is prepared in a continuous cooker using a blend of glucose syrup, sweetened condensed milk, sugar, and butterfat. The ingredients are heated in a scraped surface heat exchanger where temperature is raised to 115 degrees Celsius, 120 degrees Celsius, allowing moisture reduction and Maillard reaction for color and flavor development. The cooked caramel exits through a static mixer and flows into a deposit manifold. Caramel is applied in a controlled layer onto the surface of the moving nougat sheet. A spreader bar or leveling roller ensures even thickness, typically between 5 mm and 8 mm. The sheet, now composed of nougat and caramel, passes through a secondary cooling tunnel to lower the temperature of the caramel to a semi-firm consistency. Cooling prevents deformation and facilitates cutting. At the peanut feeding station, roasted peanuts are applied onto the tacky caramel layer. Peanuts, previously roasted at 150 degrees Celsius, 170 degrees Celsius for 20-25 minutes, and cooled, are distributed from a hopper via a vibratory feeder. They are released through multiple chutes spaced laterally to ensure even coverage. A compression roller lightly presses the peanuts into the caramel, anchoring them mechanically. Excess or misaligned peanuts are removed by a combination of rotating brushes and air jets. The layered slab, now consisting of nougat, caramel, and embedded peanuts, proceeds to the portioning station. First, longitudinal cutting blades divide the sheet into multiple lanes, matching the width of the final bars. Rotary disc blades mounted on servo arms maintain cutting precision at high speeds. Next, transverse cutting is performed with guillotine knives that are synchronized with belt speed to produce exact bar lengths. Standard bar length ranges between 80 mm and 100 mm depending on pack size. Each individual bar is spaced out on a conveyor and conveyed to the enrobing line. Enrobing is performed using milk chocolate prepared in tempering units. Solid chocolate blocks are melted in jacketed tanks at 45 degrees Celsius, 50 degrees Celsius. Melted chocolate is tempered using a 3-stage heat exchanger that brings the temperature down to 28 degrees Celsius, 30 degrees Celsius, before raising it slightly to 31 degrees Celsius, 32 degrees Celsius, optimizing crystal structure. Tempered chocolate is pumped to the enrober and flows over a curtain that uniformly coats the top and sides of each bar. The underside is coated by the bar contacting a chocolate film spread onto the mesh belt. The enrober uses a closed-loop recirculation system with a filter to remove solid debris such as peanut fragments. Chocolate viscosity is continuously monitored and adjusted by recalibrating the temperature or adding cocoa butter as needed. As the enrobed bars exit the curtain, they pass over a vibrating section that removes excess chocolate and evens out the coating. Air knives located above the belt blow off remaining drips and define the shape of the chocolate coating. Decorative top striations are formed by additional nozzles or vibrating wires that create surface patterning before the chocolate solidifies. Coated bars enter a cooling tunnel that is divided into multiple thermal zones. Temperature decreases gradually from 12 degrees Celsius to 5 degrees Celsius along the tunnel length. Air is dehumidified to prevent condensation and maintain surface gloss. Conveyor belt speed is regulated to maintain a dwell time of 10-14 minutes, allowing full crystal formation within the chocolate and ensuring coating integrity. After cooling, bars exit the tunnel and proceed directly to the wrapping system. Horizontal form-fill seal machines handle individual wrapping. Printed film is fed from a roll and shaped around the bar using a forming collar. Longitudinal seals are made with heated rollers, and transverse seals are applied with rotating jaws. Seal parameters are set according to film type, typically biaxially oriented polypropylene. Eye mark sensors on the wrapper film ensure print alignment with bar positioning. Wrapped bars are discharged from the flow wrapper and directed onto collection belts. Depending on final packaging format, bars are grouped into singles, multi-packs, or inserted into cartons. Collation is handled by diverters and indexing conveyors that control product spacing and group counts. Cartoning is performed using automatic cartoner machines that erect, fill, and close cartons in one continuous motion. Hot melt glue is dispensed by nozzle applicators to seal carton flaps. Carton size and closure mechanism are adjusted based on product format. At this stage, the complete Baby Ruth bars have undergone mechanical and thermal transformation from raw syrup, milk solids, and nut ingredients into structured, layered, enrobed, and wrapped units. From initial syrup cooking to final wrapping, all steps are continuous and synchronized by servo-driven machinery, sensor-guided conveyors, and recipe-controlled dosing systems. No manual handling is present between slab formation and wrapping. All ingredient transitions are facilitated through pumps, screw feeders, and belt conveyors. Mixing, cooking, spreading, cooling, cutting, coating, and wrapping occur in physically distinct but functionally integrated process zones. The nougat structure is controlled by syrup concentration, aeration speed, and protein matrix strength. Caramel consistency is determined by temperature profile and solids content. Peanut adhesion is achieved by compression into a semi-set caramel phase. Chocolate crystallization is stabilized by controlled tempering and gradual cooling. Final bar geometry is maintained by precision portioning and belt tracking. Line speeds are configured to produce hundreds of bars per minute, with each step calibrated for thermal load, product viscosity, mass consistency, and dimensional tolerance. The entire operation functions as a continuous flow line driven by precise thermal, mechanical, and depositional parameters. The result is a consistently shaped, layered, and enrobed chocolate bar manufactured through a sequence of interdependent, high-speed industrial systems. Tim Horton's donut production begins with a dry mix formulation containing enriched wheat flour, sugar, dextrose, non-fat dry milk, salt, leavening agents like sodium acid pyrophosphate and baking soda, and dough conditioners. These dry ingredients are stored in silos or large bagged quantities and conveyed into industrial mixers via auger-fed hoppers. Water, maintained at a controlled temperature between 26-30 degrees Celsius, is added automatically by volume through solenoid-controlled valves. The mixture undergoes a high-capacity mixing process using horizontal paddle mixers that operate for approximately 10 to 12 minutes until a smooth, elastic dough forms. Dough temperature is precisely maintained to ensure consistent gluten development. The mixed dough is transferred to a resting conveyor where it undergoes a short fermentation stage, typically lasting 10 to 15 minutes. During this period, gluten strands relax, allowing easier downstream sheeting and cutting. The dough enters a sheeting system composed of heavy-duty rollers that gradually flatten the dough to a uniform thickness, often between 8 to 12 millimeters depending on the donut type. A dusting system coats the sheet with a thin layer of flour or starch to prevent sticking. Next, rotary cutters mounted on a continuous belt use oscillating blades and die shapes to stamp out ring donuts, filled donut bases, and specialty shapes. Hole cutouts are collected via vacuum suction and reintroduced into the dough stream to reduce waste. The shaped pieces drop onto a mesh conveyor belt, which transfers them into a proofing chamber. The proofer is a humidity and temperature-controlled enclosure typically maintained at 38-42 degrees and 75-85% relative humidity. Here, yeast-leavened donuts undergo final fermentation for 35 to 50 minutes, doubling in size. Upon exiting the proofer, donuts enter a continuous fryer via an infeed belt that gently lowers each piece into the oil. The fryer is filled with high-stability vegetable shortening, held at a consistent temperature of 185-190 degrees Celsius. Conveyor arms with paddles submerge the donuts briefly before flipping mechanisms rotate them halfway through the cycle to ensure even cooking on both sides. Each donut spends 90-120 seconds in the fryer. Oil filtration systems continuously circulate and clean the oil through mechanical filters and carbon filtration media to maintain clarity and extend oil life. Excess oil is removed from the surface by air knives as donuts exit the fryer. Fried donuts transfer to a cooling conveyor, where forced ambient air reduces product temperature before glazing or filling. For ring donuts, a waterfall-style glazing system coats the tops with sugar glaze. The glazing machine contains a recirculating pump that delivers a steady curtain of glaze to ensure uniform coverage. Filled varieties proceed to an injection station. A synchronized multi-nozzle injector aligns with each donut and dispenses a precise volume of filling, such as fruit jam, Bavarian cream, or chocolate, into the center of the pastry using piston-driven pumps. Fill volumes are regulated down to the gram for product consistency. Specialty donuts requiring additional coatings, such as powdered sugar or cinnamon sugar, enter a rotating tumbler. The tumbler's perforated drum allows excess sugar to fall through while evenly applying the coating as the donuts rotate inside. Sensors monitor rotation speed and coating application rate. For chocolate or icing-topped varieties, donuts pass through a curtain enrobing system or a top-down depositor. The enrobing system consists of a tempering kettle and a heated pump that maintains the chocolate or icing at its working viscosity, typically around 40-45 degrees Celsius. Topping depth is controlled by belt speed and curtain thickness. Donuts requiring sprinkles or toppings are conveyed beneath a waterfall depositor or rotary sprinkler. The toppings are dispensed from a vibrating hopper that ensures even spread. Static charge may be applied in some systems to increase topping adhesion to the wet icing. Once decorated or filled, donuts proceed through a spiral cooling tower. The spiral conveyor allows a compact vertical footprint while offering extended cooling time, typically 15 to 20 minutes. Forced air circulation removes residual heat, allowing products to stabilize before packaging. Each donut then moves through a vision-based quality control system. High-speed cameras scan for defects in size, color, fill placement, or topping consistency. Items outside. Tolerants are rejected automatically using pneumatic pushers. Qualified donuts are then grouped by variety and type using a servo-controlled collation system. Products are aligned into lanes and counted by photoelectric sensors, preparing them for packaging. Packaging is handled by an automated tray loading system. Flat-folded paperboard trays are erected using mechanical arms, and donuts are placed inside via pick-and-place robots with suction grippers. For assorted packs, robotic arms select donuts by type from buffer conveyors. Trays proceed to a lid applicator station, where pre-folded lids are pressed and sealed using glue jets or heat-sensitive adhesives. For retail cases, sealed trays are grouped and shrink-wrapped using polyolefin film, which is cut, wrapped, and heat-shrunk in a tunnel oven operating at around 160 degrees Celsius. Each finished pack receives an inkjet-printed date code and batch number from a variable data printer. The printer adjusts to the motion of the conveyor, ensuring clear marking without interrupting product flow. Packaged products are conveyed to palletizing stations. Robotic palletizers, equipped with vacuum or mechanical grippers, stack trays in precise layer patterns onto standard pallets. Slip sheets may be inserted between layers for stability. Full pallets are wrapped using a rotary arm stretch wrapper. The film roll is tensioned to apply a tight wrap without deforming the boxes. Wrapped pallets are transferred to refrigerated holding or shipping docks for distribution. Throughout the process, programmable logic controllers synchronize machine timing, belt speeds, pump volumes, and thermal settings. Human-machine interface panels monitor all parameters and log production data. The entire line is modular and scalable, allowing simultaneous production of multiple donut types. Conveyors interlink each station, minimizing manual transfer and optimizing flow. Changes in donut type or size are handled through automated tool change, systems, or quick swap components. Pre-programmed recipes stored in the central control system reconfigure the line settings within minutes. Staging silos and ingredient feeders are equipped with load cells to precisely meter dry ingredients. Liquid ingredients are stored in jacketed stainless steel tanks with inline agitators to prevent settling or stratification. The dry and liquid ingredient streams merge at the mixer's inlet via butterfly valves controlled by digital weigh scales. The dosing accuracy ensures batch-to-batch uniformity, critical for dough performance during proofing and frying. Proofing chambers are equipped with belt elevation systems that loop the dough pieces through multiple horizontal levels. Fans and humidifiers ensure even air distribution, and digital probes record temperature and humidity in real time. Fryers are segmented into temperature zones with independent heating coils managed by thermocouple feedback. This zoning ensures even coloring across all donut types, regardless of fill or topping. Oil levels are maintained by float-based control valves, and inline filtration runs continuously. Spent oil is periodically replaced using external storage tanks connected by insulated pipelines and pneumatic pumps. The icing station includes a recirculation tank and a filtration mesh that removes solid particles from reused icing. Viscosity is measured using a rotational viscometer integrated into the circulation loop. Decorative elements such as drizzle patterns or text are applied using programmable depositor heads, which trace patterns based on CAD instructions and synchronize with conveyor speed to ensure alignment. Filled donuts pass through an X-ray inspection tunnel, identifying underfilled or foreign material contaminated units. Rejected items are diverted to a side conveyor for manual review. Donuts for seasonal assortments are coded with quick response QR markers beneath their trays allowing downstream distribution centers to sort mixed lots via machine vision systems and RFID tracking. Dunkin Donuts. Donut production begins with dry ingredient blending, high-protein wheat flour, dextrose, sugar, soy flour, non-fat milk powder, salt, dough conditioners, and chemical leavening agents such as sodium bicarbonate and monocalcium phosphate are measured by weight and transferred into large-capacity industrial mixers using pneumatic conveying systems or gravity-fed hoppers. Liquid ingredients, including water, liquid shortening, and egg yolk solids, are preheated and pumped into the mixer via metered dosing systems. Water temperature is held between 27 to 30 degrees Celsius to activate gluten formation without overheating. Mixers equipped with high-torque planetary paddles operate in timed cycles to combine the dough, typically lasting 8 to 12 minutes. Dough temperature is monitored continuously with inline probes. Target final dough temperature is around 27 degrees Celsius for yeast-raised donuts to ensure optimal proofing behavior. Once mixed, the dough is transferred to a resting trough conveyor for gluten relaxation and hydration equilibrium, allowing for consistent sheeting performance. The rested dough moves to a multi-stage sheeting system composed of compression rollers that gradually reduce thickness in incremental stages. Roller gap adjustments are motorized and recipe controlled. Final sheet thickness is typically 9-11 mm, depending on the donut style. A light dusting system applies fine cornstarch or rice flour across the dough sheet surface to prevent sticking. The sheet then feeds into a rotary die cutter system. The cutter contains interchangeable dies for different donut varieties, including ring shapes, filled rounds, bars, and novelty shapes. The cutting drum rotates in synchronization with the conveyor to ensure clean, high-speed cuts. Cut donuts are transferred onto wire mesh proofing trays by vacuum-assisted pick-and-place systems. The trays are automatically stacked into a multi-tiered conveyor rack that moves through a temperature and humidity-controlled proofing chamber. Proofing conditions are held at 38 to 40 degrees Celsius, with 80-85% relative humidity for 35 and 45 minutes. Within the proofer, dough pieces rise and expand due to yeast activity. Conveyor motion is timed so that each tray spends the same duration in the chamber. Sensors track fermentation progression using size and weight benchmarks. After proofing, trays enter an automated unloading system that transfers the dough pieces onto a fryer in-feed belt. Frying oil is a refined, high-stability vegetable shortening maintained at 185-190 degrees C. The fryer contains a dual-zone heating configuration and a submersion system using paddle arms that guide and flip the donuts midway through frying. Total fry time is approximately 90 seconds. Ring donuts are flipped automatically after 45 seconds by rotating bars. Filled donut bases remain face up to maintain a flat bottom. Oil turnover is managed through continuous filtration using a centrifugal separation system and micron-level mechanical filters to remove particulates. As the donuts exit the fryer, excess oil is removed by angled mesh belts and compressed air nozzles. Products then travel along a cooling conveyor system with ambient airflow, reducing surface temperature below 35 degrees Celsius before handling. Ring donuts destined for glazing pass under a waterfall-style glazing station. The glazing tank contains a high-shear mixer that maintains solution homogeneity. A recirculating pump delivers glaze to a curtain nozzle that flows over the donuts. Excess glaze drains back into the holding tank through a mesh screen. Filled donuts proceed to a pressurized injection system. Each donut aligns with a dual or quad nozzle filler head that penetrates the side or bottom. Piston pumps dispense fillings such as jelly, cream, or custard with precision-controlled volume, typically 18 to 25 grams per unit. After filling, donuts requiring icing are transferred. to a top-down depositor. This system uses heated reservoirs that keep icings at 40 to 45 degrees Celsius. Servo-controlled valves open and close based on donut presence detected by photoelectric sensors. Depositor heads apply a measured layer of icing across the top surface. For varieties requiring toppings, donuts travel under a vibratory topping applicator. Toppings such as chopped peanuts, sprinkles, or coconut shavings are dispensed via a rotating auger or oscillating tray, which evenly distributes material across the icing surface. Adhesion is achieved by timing the topping deposit immediately after icing application. Powder-coated or sugar-rolled donuts are conveyed into a rotating tumbler drum. A controlled feed of granulated or powdered sugar enters through a dosing hopper. The drum rotates at a calibrated RPM to coat donuts uniformly without damaging their structure. Fine mesh filters remove sugar clumps from the recirculation stream. Donuts with drizzle designs undergo a separate decoration process using linear motion gantry arms. These arms carry nozzles that deposit thin lines of icing, chocolate, or flavored syrup in programmed patterns. Motion control algorithms synchronize nozzle movement with conveyor speed for accurate designs. Post-decoration, all donuts pass through a spiral cooling tower. This vertically stacked conveyor system allows compact, high-capacity cooling with continuous airflow. Residence time is typically 15 to 20 minutes, allowing toppings to set and fillings to stabilize. Donuts exit the spiral cooler and enter a high-speed vision inspection system. Industrial cameras, mounted above and to the side, scan each product. Parameters such as size, color, symmetry, icing coverage, and fill injection marks are analyzed in real time. Out-of-spec items are removed via air-jet ejection systems. Acceptable donuts are organized into lanes using servo-driven diverter arms. Grouping is based on variety and pack size. Collation belts accumulate donuts into patterns that match tray cavities. Packaging begins with automatic tray erecting. Flat paperboard blanks are fed into a forming unit that applies glue and folds trays into shape. Form trays move beneath pick-and-place units with vacuum suction cups that deposit donuts into each cavity. Assorted variety packs are assembled by robotic gantries with product recognition software. These systems pull donuts from buffer conveyors and place them according to pre-programmed variety maps. Tray sealing depends on the product format. Some are closed with plastic lids, applied and snapped into place by mechanical presses. Others use film sealing units with heated jaws that apply plastic film over the tray and bond it along the edges. Packaged trays are labeled using thermal inkjet printers. Labels include production codes, variety, and timing information. Alignment sensors ensure accurate label placement without interrupting conveyor flow. Trays are loaded into cardboard master cases using side-loading systems. Collapsible cases are automatically erected from flat blanks and fed into the loading station. Case flaps are glued and sealed using hot melt adhesive heads. Filled master cases are conveyed to a robotic palletizer. A vision-guided robot stacks cases in alternating patterns for load stability. Slip sheets are added at programmed intervals to separate layers. The stack height is optimized for transport requirements. Each completed pallet is wrapped with stretch film using a rotary arm wrapper. The arm spins around the stationary pallet, tensioning the film for secure transport. Film overlap and wrap count are controlled digitally to match load size. Wrapped pallets are labeled with barcoded identification tags applied by robotic labelers. Pallets then enter a gravity-fed conveyor line toward refrigerated loading docks or cold storage. Throughout the production line, operations are governed by a distributed control system. Programmable logic controllers handle station-level automation, while supervisory control and data acquisition systems log all machine parameters, production metrics, and alarms. recipe management software controls all batch-dependent variables, including mixing time, proofing duration, fryer temperature, fill weights, and topping dosages. Each donut type has a profile stored in the system, allowing for rapid product changeovers with minimal downtime. Dry ingredient silos are equipped with level sensors and load cells. Refilling is coordinated with automated delivery systems to ensure continuous availability. Ingredient dosing systems operate under gravimetric and volumetric control for precise formulation. Liquid shortening is held in insulated tanks with inline heaters and agitators to maintain uniform viscosity. Delivery lines are jacketed and circulate hot water to prevent solidification. Pumps use variable frequency drives to adjust flow rate based on batch requirements. Filling hoppers for creams and jellies are jacketed for temperature control and agitated to prevent phase separation. Fill viscosities are monitored using inline viscometers, and pressure is regulated to prevent overfill or underfill. Proofing conveyor belts are made from non-stick, food-grade materials and guided on multiple horizontal tiers. Air circulation is forced through dampers to ensure uniform proofing across all trays. Temperature and humidity are logged for each cycle. Fryer systems include zoned heating elements and oil curtain barriers to minimize heat loss. Oil flow rate and turnover frequency are tracked by volumetric flow meters and recirculation pumps. Air knives at the fryer exit are powered by centrifugal blowers with adjustable nozzles. Their position and pressure are calibrated to strip excess oil without disturbing surface structure or toppings. Glazing tanks are cleaned and refilled on a timed schedule using CIP circuits. Glaze viscosity is maintained with real-time temperature feedback loops and monitored by rotational viscometers. All conveyors, transfer points, and topping stations are modular and mounted on quick-release brackets, allowing reconfiguration for new product lines or seasonal variations. The manufacturing process for Chips Ahoy. Cookies begins with precise dry ingredient batching. Key components include enriched wheat flour, sugar, brown sugar, baking soda, salt, and emulsifiers. These dry ingredients are stored in silos or super sacks and automatically dispensed via auger-fed feeders into high-capacity weigh hoppers. Load cells measure each ingredient to exact tolerances before being discharged into the mixing system. In parallel, liquid ingredients are prepared. These include water, high fructose corn syrup, molasses, glycerin, and vanilla flavoring. Liquid fats such as palm or soybean oil are stored in heated, jacketed tanks and pumped through insulated lines to maintain target viscosity. Liquid dosing is controlled using flow meters and metered pumps integrated into the batch control system. All ingredients are conveyed to an automated horizontal batch mixer. The mixing cycle follows a strict sequence: creaming of fats and sugars first, followed by the introduction of liquid components, then gradual incorporation of dry flour-based ingredients. Mixing speed and time are controlled by PLCs based on the dough formulation. Dough temperature is maintained between 20 octati to preserve texture consistency. Once the base dough is formed, chocolate chips are added. These are stored in climate-controlled hoppers to prevent melting or clumping and are added during the final low-speed mixing phase to avoid breakage. Chip loading is calibrated by weight to ensure uniform distribution across the batch. Mixed dough is discharged from the horizontal mixer into a dough handling system, which typically includes a feed conveyor and a rotary chunker. The chunker breaks large volumes into manageable portions for downstream processing. Dough portions are conveyed to the forming line. Portioned dough enters an extrusion-based depositor system. The depositor uses servo-controlled pistons to extrude dough through circular nozzles onto a moving oven band. Each cookie unit is dropped at exact intervals to maintain spacing and size. Depositor nozzles are non-stick coated and fitted with sensors to detect flow irregularities. The formed dough pieces move directly into a multi-zone continuous baking oven. The oven band is typically a steel mesh or solid band, depending on desired bottom texture. The oven is divided into several independently controlled thermal zones, with temperatures ranging from 180 degrees C to 230 degrees C. Baking duration is precisely set, typically between 6 to 10 minutes. As cookies move through the oven, moisture evaporates rapidly in the early zones, setting the outer structure. Later zones apply radiant and convection heat to develop interior texture and caramelization. Infrared sensors monitor surface temperature, and humidity sensors measure exhaust moisture for quality tracking. Exiting the oven, cookies pass onto a series of wire mesh cooling conveyors arranged in serpentine or spiral layouts. Ambient forced air circulates across multiple tiers to reduce cookie temperature from above 112 degrees to below 35 degrees within 8 to 12 minutes. Cooling speed is critical to avoid cracking or warping. Cooled cookies then enter a vision inspection system. High-speed cameras and image processing software detect dimensional conformity, color uniformity, chip distribution, and surface defects. Defective units are ejected via pneumatic actuators or diverter arms. Passing inspection, cookies are aligned into lanes via vibratory feeders and belt diverters. Lane alignment facilitates entry into the packaging system. Product counters track units per minute and signal robotic collators when batch quantities are ready. Packaging begins with slug loading. Cookies are grouped into vertical stacks, or horizontal slugs using indexing belts and pushers. Slug formation is synchronized with wrapper film feed using registration marks and encoder-driven rollers. Each cookie slug is pushed into a horizontal flow wrapper. Wrapping film is heat sealable and typically polypropylene based with a moisture barrier coating. The film unwinds from a roll and wraps around the cookie slug as it is propelled forward. Longitudinal and transverse heat sealers create the fin seal and end seals in rapid succession. Sealed packs exit the flow wrapper and pass under an inkjet coder that prints date codes and batch identification using edible grade ink. The print head operates in coordination with conveyor speed to maintain legibility. Wrapped packs are conveyed to cartoning machines. Here, cartons are formed from flat blanks by mechanical arms and glue stations. Wrapped slugs are side-loaded into open cartons, which are then closed, sealed, and printed with product and batch information. Cartons are grouped into shipping trays using automated case packers. These machines use robotic pick-and-place arms or pusher mechanisms to load cartons into corrugated cases. The case flaps are sealed using hot melt glue or tape applicators. Full cases move to a robotic palletizer station. Cases are arranged into a predetermined pallet pattern, layer by layer. Slip sheets may be added automatically between layers to improve load stability. Each layer is compressed slightly to ensure uniform height. Completed pallets are conveyed to a stretch wrapping station. A rotating arm or turntable applies plastic film under tension, with pre-stretch rollers ensuring optimal film usage and secure load containment. Wrapping cycles are adjusted for pallet height and weight. Each pallet receives a scannable barcode label printed by an industrial thermal printer. Labels are applied on two adjacent sides for redundancy. Pallet data is logged into the central warehouse system for tracking and inventory. Control. Ingredient replenishment is coordinated with automated inventory management. Raw material silos and liquid tanks are equipped with level sensors and integrated into the batch scheduling system. Ingredient usage is monitored in real time to prevent production interruptions. Throughout the production line, all mechanical systems are controlled by PLCs communicating through an industrial Ethernet network. Recipe parameters are stored in a central HMI interface, allowing operators to switch product types by loading preset programs. Mixing cycle parameters include motor torque, bowl rotation speed, and batch temperature. If values deviate from preset ranges, alarms are triggered, and production can be halted for correction. Chocolate chips are dispensed through vibratory feeders equipped with mass flow sensors. Feed rate is adjusted automatically to match dough throughput. Chips are gently folded into the dough using planetary paddles to preserve shape and prevent smearing. Extrusion depositors are cleaned and recalibrated between batches. Nozzle calibration uses laser measurement systems to verify uniform drop size across all channels. The baking oven includes thermal profiling tools, traveling temperature probes mounted on dummy cookies that measure time and temperature exposure across zones. These profiles are compared to standard references to ensure bake uniformity. Airflow in the cooling conveyor is managed by adjustable baffles and high-volume blowers. Zones are configured to prevent condensation or localized overheating, which could impact texture. Packaging film is spliced automatically using a festoon buffer system, allowing roll changes without stopping the wrapper. Splice detection sensors verify successful transfer and trigger rejection of the transition pack if required. Flow wrappers are equipped with film tracking systems using edge guide sensors to maintain alignment. Tension controllers manage unwind force to prevent film distortion. Cartoning machines feature vision systems that verify correct pack orientation before loading. Misoriented or missing packs trigger reject mechanisms that divert affected cartons to inspection lanes. Case packers use Delta-style robots with suction grippers or mechanical claws. Gripping pressure is adjustable to avoid crushing while maintaining speed. Robot arms operate on articulated joints with sub-millimeter precision. Palletizer systems incorporate automatic pallet dispensers and slip sheet feeders. Gripper heads are interchangeable for different case sizes and stacking formats. Production data, including line speed, output volume, defect rate, and downtime, is continuously recorded and transmitted to a manufacturing execution system. Reports are generated hourly for supervisory review and performance tracking. Temperature-sensitive ingredients, such as chocolate chips and syrup, are stored in climate-controlled zones. Delivery lines use nitrogen flushing or vacuum seals to prevent oxidation and contamination. Finished goods are staged in a climate-regulated buffer zone before loading. Inventory movement is tracked via RFID-tagged pallets, which interface with the logistics management software. Ben & Jerry's ice cream is produced by combining dairy and dry ingredients in a multi-stage mixing and freezing process that integrates inclusions and variegates at high precision. The process starts with the batching of the base mix, which is composed of whole milk, cream, liquid sugars, and dry solids such as stabilizers and emulsifiers. Milk and cream are pumped from cold storage tanks into insulated blending vessels. These vessels are jacketed for thermal control and fitted with slow-speed agitators. Liquid sucrose or invert sugar is added next through metered flow lines connected to bulk sugar tanks. Dry components, including milk powder, gore gum, and mono and diglycerides, are introduced through a powder induction system located at the top of the vessel. Powder is drawn into the vortex of the liquid mix through vacuum pressure and blended evenly by the impeller. Once fully blended, the base mix is transferred through sanitary piping to the pasteurization unit. Pasteurization is carried out using a high-temperature, short-time system where the mix is rapidly heated to a fixed temperature above 80 degrees Celsius. The heated mix is held in a thermal chamber for at least 25 seconds and then cooled immediately through a regenerative heat exchanger. This brings the temperature down to 4 degrees Celsius before the mix reaches the aging tanks. Aging tanks are insulated vertical silos equipped with slow-speed agitators to maintain mix homogeneity. The mix is stored here for a minimum of 4 hours and up to 24 hours depending on formulation. During aging, fat crystallization begins and proteins fully hydrate, which improves overrun stability and mouthfeel in the final product. After aging, the cold mix is pumped to the flavoring station. At this point, base flavor ingredients such as vanilla extract, chocolate liquor, or fruit puree are injected in line using precision dosing pumps. Each flavor component is calibrated to match the target formulation and is verified through flow sensors that monitor mass per second. From here, the flavored mix enters the continuous freezer. Continuous freezers are scraped surface heat exchangers that pump the mix through a cold barrel while simultaneously injecting air. The inner barrel surface is chilled using ammonia-based refrigerant and fitted with rotating scraper blades that prevent ice buildup. As the mix travels through the barrel, it begins to freeze on the walls and is continuously scraped into a fine frozen slurry. The injected air creates overrun, which determines the density of the ice cream. Overrun is adjusted by controlling the airflow rate and pump speed and is generally kept below 50% for super premium texture. Frozen mix exits the continuous freezer at a semi-solid state and enters the ingredient feed system. This system consists of a hopper that holds dry inclusions such as cookie chunks, brownie pieces, or chocolate chips. A positive displacement auger pulls inclusions from the hopper and meters them into the ice cream flow at a controlled rate. Each piece is fed in without breaking or melting due to the low product temperature and synchronized speed control. At this stage, variegates such as caramel swirls, fudge ripples, or peanut butter ribbons are also added. These are introduced through a separate pump system that deposits the variegate in a continuous stream alongside the ice cream stream. The product then passes through a laminar blending manifold that gently folds the components together without excessive shear. The structure of swirls is preserved using channelized flow paths that direct streams into the center of the bulk flow. The fully mixed and frozen product is directed to the filling station where pre-formed containers are loaded onto an indexed carousel. Each container is aligned with a filling head that dispenses a measured volume of ice cream. Fill rate is governed by a servo-controlled piston that maintains consistent deposit weight. Once filled, the container advances to a leveling station where a rotating plate smooths the surface of the product. Some variants receive additional toppings at this stage, such as crushed nuts or fudge drizzle, which are dispensed using vibratory feeders or rotary nozzles. Filled containers proceed to lidding, where high-speed arms place and seal plastic lids onto each pint. The lids are pressed down with calibrated force to create a friction seal. The sealed pints then move to the hardening tunnel, which is a spiral freezer maintained at temperatures below -30 degrees Celsius. The product remains in this tunnel for approximately 3 hours to achieve full core hardening. Cold air is forced over the pints at high velocity to extract latent heat uniformly. Upon exiting the hardening tunnel, the pints are conveyed to the coding station where batch information is printed on the lid or bottom using inkjet printers. Following this, the pints enter the cartoning system, where mechanical pushers insert them into printed cartons for multi-pack orders. For single packs, they are collated into crates using pneumatic actuators that align units for stacking. Each crate is conveyed to a palletizing station where robotic arms stack the product according to a programmed matrix. The pallets are then shrink-wrapped and labeled before being transferred to the frozen storage warehouse. Throughout the process, temperatures are continuously monitored and recorded at all key points, including mix tanks, freezers, hoppers, filling heads, and hardening zones. Every production step is automated using programmable logic controllers connected through an industrial network. Sensors measure flow rates, temperature profiles, viscosity, deposit weights, inclusion counts, and air pressure in real time. Adjustments are made automatically to maintain consistency across thousands of units per hour. The mix composition defines final mouthfeel and thermal behavior. Pasteurization ensures phase uniformity and emulsion stability, Aging promotes protein hydration and crystal growth. Freezing governs ice crystal size and air distribution. Inclusion delivery is timed precisely to avoid damage. Variegate folding is optimized for aesthetic and structural preservation. Product texture depends on water content, fat structure, and ice distribution. Overrun level directly affects scoop resistance and volume yield. Inclusion integrity depends on size, shape, and moisture content. Ripple distribution is determined by variegate viscosity and flow channel geometry. Final hardness is a function of exit temperature and hold time in the spiral freezer. Containers are designed to withstand both vacuum during filling and pressure changes during freezing. Lid placement requires precise tolerance to avoid deformation during hardening. Pallet loads are structured to prevent toppling and to allow airflow in the warehouse. All mechanical movements are synchronized to upstream and downstream operations to prevent backup or starvation in the line. Line cleaning occurs between flavor changes using automated clean-in-place systems that flush all internal surfaces with heated detergent followed by sterile rinse. Tanks, pipes, freezers, and filling heads are cleaned without disassembly using pressurized flow circuits. Wastewater is filtered and returned to treatment before discharge. No part of the Ben & Jerry's production process is manual once ingredients are loaded into storage tanks. Ingredient handling, dosing, mixing, heating, cooling, aerating, folding, depositing, sealing, hardening, coating, packaging, and stacking are carried out in a fixed sequence controlled by machine logic. Dairy Queen Soft Serve is created through a multi-phase process that begins with the formulation of a liquid dairy mix. The mix consists of milk solids, cream, sweeteners, stabilizers, and emulsifiers, which are combined in stainless steel batching tanks. The tanks are equipped with slow-speed agitators that maintain uniform suspension of all components during hydration. Milk and cream are pumped from chilled storage tanks using sanitary centrifugal pumps. Sugar is conveyed from bulk hoppers to the mixing tank via auger-fed systems. Stabilizers and emulsifiers such as mono and diglycerides, gargum, and carrageenan are introduced through powder induction ports. The dry ingredients are pulled into the vortex of the circulating liquid using a vacuum venturi system mounted above the mixing tank. The blended mix is agitated until all solids are hydrated and evenly distributed. Temperature in the mixing tank is gradually raised to above 65 degrees Celsius using a jacketed steam heating system. Once the desired blending temperature is reached, the mix is pumped to the pasteurization unit through insulated transfer piping. Pasteurization occurs using a plate heat exchanger which brings the liquid to 80 degrees Celsius or higher for a controlled retention time. After thermal treatment, the mix is cooled immediately to 4 degrees Celsius through countercurrent heat exchange. The chilled liquid is transferred to aging tanks, where it remains under gentle agitation for 8 to 12 hours. During aging, the fat particles begin to partially crystallize, which stabilizes emulsion and improves body and texture. Proteins and gums fully hydrate in this period, which enhances viscosity and mix performance during freezing. The aged mix is then directed to a homogenization unit. Homogenization is performed in 2 stages using a high-pressure valve assembly. In the first stage, fat globules are broken down by hydraulic shear at pressures above 1,500 pounds per square inch. The second stage ensures dispersion of remaining aggregates through pressure equalization at lower intensity. The homogenized mix achieves a uniform fat droplet size, which improves smoothness and prevents creaming. After homogenization, the base mix is cooled again to 4 degrees Celsius and held in refrigerated tanks until needed for production. When ready, the liquid is pumped to filling stations for intermediate packaging or loaded into distribution tanks if sent to retail locations. In stores, The liquid mix is fed directly into soft serve machines, which perform final freezing and aeration. The machines contain a freezing cylinder surrounded by a refrigerant coil. The mix is pulled from the refrigerated hopper into the freezing barrel using an auger system. As the auger rotates, it scrapes the interior barrel surface and simultaneously compresses the mix forward while incorporating air. Air is introduced through a calibrated orifice that meters flow based on pump rate. The ratio of air to mix is tightly controlled to produce the desired overrun, which is typically between 30 and 45%. This ensures a light texture without exceeding melt resistance limits. As the mixture moves through the freezing barrel, it begins to crystallize along the interior surface. Scraper blades continuously remove frozen product and fold it into the flowing stream. The barrel is chilled using a sealed system filled with R404A or similar food-grade refrigerant. The expansion valve regulates evaporator pressure to maintain a barrel wall temperature near -10 degrees Celsius. The partially frozen soft serve exits the cylinder at a semi-solid state with uniform aeration and consistent temperature. The product is dispensed directly from the extrusion nozzle into cones or cups using a gravity-fed or pump-assisted mechanism. Flow rate is controlled by a handle-actuated valve that opens a piston or gate at the nozzle outlet. The nozzle is shaped to produce the distinctive swirl pattern through laminar flow and rotational motion. The final product has a temperature near -6 degrees Celsius and maintains this state for several minutes under normal ambient conditions. No post-processing or hardening occurs after extrusion. Flavor variations are achieved through pre-flavored base mixes or inline syrup dosing. For syrups, a separate pump introduces concentrated flavor into the liquid stream before freezing. Syrup flow is matched to mix rate using flow meters and feedback control. Chocolate-dipped variants are produced by inverting the cone into a vat of liquid coating held at a fixed temperature. The coating solidifies upon contact with the cold, soft-serve surface. The solid layer forms within 2 seconds due to the sharp temperature gradient and the high coconut oil content in the coating formula. Multi-flavor twist products are created using a dual cylinder system. Each freezing barrel processes a different flavor. Both barrels feed a common extrusion head that contains 2 internal chambers. A Y-shaped nozzle merges the 2 flows at the outlet while maintaining separation. The twist effect is generated by the natural helical movement during downward extrusion. Inclusion-based variants such as candy or cookie pieces are added manually at the serving point. Toppings are not incorporated during freezing as they would interfere with scraper operation and pump integrity. Specialty formats such as Blizzard products use the same base soft serve dispensed into mixing cups. Solid inclusions are added from bulk hoppers and mixed using a vertical blender with a custom blade. The mixer agitates the entire volume briefly and evenly distributes solid inclusions without altering temperature or structure. The mix used for Dairy Queen soft serve has a fat content near 5% and milk solids non-fat between 11 and 12%. Stabilizers control ice crystal growth during freezing and maintain uniform viscosity during storage. Emulsifiers assist in fat dispersion and reduce weighing during freezing. Overrun is mechanically induced by synchronized air injection and auger transport. Storage tanks are cleaned with automated CIP cycles between production runs. Freezing cylinders are cleaned manually or with clean-in-place systems depending on model configuration. Syrup dosing systems are flushed with warm water after each flavor change. Coating vats are reheated and filtered periodically to maintain viscosity and clarity. All equipment involved in Dairy Queen production is constructed from stainless steel with hygienic welds and polished surfaces. Flow paths are sealed using tri-clamp fittings and silicone gaskets. Pumps use sanitary diaphragms or lobe rotors for gentle handling. Freezing units are maintained at fixed compressor settings based on product load and ambient conditions. The mechanical structure of the soft serve is defined entirely by air cell dispersion, fat matrix stability, and ice crystal size. Each parameter is determined by process inputs such as homogenization pressure, barrel residence time, and freezing surface temperature. No component of the product is batch frozen or aged at the point of service. Every portion is frozen continuously on demand and delivered immediately for consumption. Structural integrity is preserved through shear controlled mixing and precise overrun regulation. Nestle ice cream production begins with bulk ingredient staging in temperature-controlled storage silos. Whole milk is held at 4 degrees Celsius in insulated stainless steel tanks fitted with agitators to prevent separation. Cream is stored separately in jacketed vessels and maintained at a consistent viscosity for accurate metering. Granulated sugar is housed in dry ingredient silos connected to the batching system via enclosed auger conveyors. Formulation is initiated by transferring milk and cream to the primary blending tank using positive displacement pumps with flow meters. The tank is jacketed and equipped with high shear agitators that disperse solids efficiently into the liquid phase. Sugar is dispensed from the silo using screw feeders that meter flow by weight. Dry milk solids are pulled into the tank through a Venturi adductor mounted on a recirculation loop. Stabilizers including guar gum and carrageenan are introduced as dry powders via a sealed hopper with rotary valve discharge. Once all components are loaded, the mix is agitated at low speed while steam is applied to the tank jacket to raise temperature to approximately 65 degrees Celsius. This step ensures solubilization of dry materials and begins the hydration of stabilizing agents. When the target temperature and viscosity are achieved, the mix is routed to the pasteurization system through a network of sanitary process piping. Pasteurization is carried out in a plate heat exchanger that subjects the mix to a thermal profile reaching 83 degrees Celsius. Holding occurs in a tubular section sized for 30 seconds residence time at peak temperature. The mix is then immediately cooled to 4 degrees Celsius using a countercurrent flow of chilled water or glycol solution. The cooled mix is sent to a set of aging tanks for further stabilization. Aging tanks are vertical silos fitted with slow-speed agitators to maintain uniformity without air incorporation. Mix resides in the tanks for a minimum of 4 hours and often up to 24 hours, depending on product formulation. During aging, the fat crystals begin to nucleate and proteins reach full hydration, which contributes to improved, overrun, and final texture. Before freezing, the aged mix is pumped through a high-pressure homogenizer that operates in 2 stages. The first stage uses a narrow orifice under 2,000 pounds per square inch to break fat globules into submicron particles. The second stage at reduced pressure eliminates aggregates to produce a fully dispersed emulsion. Homogenization ensures improved creaminess and resistance to fat separation during storage. Flavoring is performed in-line immediately before freezing using precision metering pumps. Flavor oils, cocoa solutions, coffee concentrates, and fruit essences are introduced via multiple injection ports into the flow stream. Flow sensors and control valves maintain exact volumetric dosing. Color additives are similarly introduced where required for specific variants. The flavored mix enters a continuous freezer, which consists of a horizontal, scraped surface heat exchanger. The interior barrel is cooled externally by a closed-loop ammonia system that maintains wall temperature below -25 degrees Celsius. The barrel is fitted with a rotating dasher that scrapes frozen product off the wall while mixing it with incoming liquid. air is injected through a calibrated orifice located near the inlet, which determines the level of overrun. Overrun in Nestle ice cream is typically maintained between 40% and 60% depending on the product line. The level of air is controlled by adjusting air pressure, dasher speed, and mix feed rate. Low overrun varieties are set below 40% for premium texture, while novelty products may be aerated to a higher extent for volume efficiency. As freezing proceeds, the product reaches a semi-solid state and exits the freezer through a pump that delivers it to the ingredient blending system. Solid inclusions such as chocolate chunks, cookie dough pieces, fruit particulates, or caramel bits are stored in hoppers above the blender. Each inclusion is gravity-fed into a feed auger that meters pieces into the ice cream stream in real time. The blending unit incorporates the inclusions into the flow path using horizontal paddles that avoid crushing fragile components. The feed rate of inclusions is electronically synchronized with the freezer output to maintain uniform distribution. Inclusion size and moisture content are tightly controlled to ensure structural integrity and to prevent bleeding or hardening after freezing. Products that require variegates such as chocolate fudge, caramel, or fruit syrup receive them at a second manifold downstream of the inclusion blender. A peristaltic pump draws variegate from a chilled tank and injects it through a fixed nozzle into the center of the ice cream flow. The pipe downstream is segmented to create controlled turbulence that folds the variegate through the product without mixing it completely. Once all ingredients are combined, the product moves to the filling station through a flexible insulated hose. Depending on the format, the product is filled into cups, tubs, cones, or novelty molds using piston fillers or rotary valves. For cups and tubs, the ice cream is deposited directly into pre-formed containers lined up on an indexing conveyor. Fill volume is precisely managed through a servo-controlled drive connected to the piston stroke length. After filling, surface leveling is performed by mechanical scrapers or rotating wipers depending on the container geometry. Some formats receive additional toppings such as syrup drizzles or solid garnish, which are deposited using vibratory trays or robotic arms. The containers then proceed to the lidding station, where lids are applied using pneumatic cylinders and heat or pressure sealing mechanisms. Filled and sealed units are then transferred into the hardening tunnel, which is a spiral or straight line blast freezer maintained at -35 degrees Celsius or lower. The air velocity within the tunnel is controlled by multiple high-speed fans and directed across the containers in a cross-flow pattern. Residence time in the hardening tunnel varies between 30 minutes and 3 hours, depending on product size and thermal load. During hardening, the unfrozen water content solidifies completely and the overrun structure becomes locked in place. Ice crystal growth is minimized by rapid freezing, which prevents graininess and ensures smooth texture. Hardening is considered complete when core temperature of the product reaches below -18 degrees Celsius. Once hardened, products are ejected from the tunnel and conveyed to the packaging line. For multi-pack items, individual units are collected into groups by mechanical diverters and placed into cartons by robotic pick-and-place systems. Cartons are formed from flat blanks using hot melt glue and folded by rotary formers. Cartons are coded with batch information using thermal inkjet printers. Carton product proceeds to case packing, where cartons are loaded into corrugated cases using side-load or top-load machines. Cases are sealed using tape or glue and labeled with destination and tracking codes. Finished cases are conveyed to automated palletizing stations, where they are stacked using articulated robotic arms onto wood or plastic pallets. Pallet patterns are selected by software based on carton size and unit weight to maximize stability and airflow in cold storage. Stacked pallets are shrink-wrapped with polyethylene film and transferred to blast freezers for holding before distribution. Final storage temperature is maintained at minus 28 degrees Celsius to minus 30 degrees Celsius with continuous airflow to prevent warm zones. The entire process from raw ingredient batching to final frozen storage is controlled by distributed PLC systems that communicate over industrial Ethernet. Parameters such as flow rate, temperature, pressure, inclusion count, overrun, and fill weight are monitored in real time. Feedback loops allow self-correction of dosing systems and line speed synchronization. No manual handling occurs at any stage after ingredient delivery. Ingredient silos, mix tanks, pasteurizers, homogenizers, freezers, blenders, fillers, tunnels, conveyors, and packers are all enclosed and automated. Cleaning is performed using clean-in-place systems that circulate caustic, acid, and rinse water through the entire process loop. Each product specification includes parameters for viscosity, Brix value, fat content, solids non-fat, pH, overrun, inclusion percentage, swirl concentration, core temperature, and packaging weight. All values are logged per batch and validated against product standards before release. Nestle ice cream is defined by tightly regulated thermal transitions, physical dispersion of fat and air, inclusion integrity, and packaging precision. The resulting product has a defined melt curve, scoop resistance, and storage life, which are engineered through material control and mechanical process sequencing. No process stage is isolated or batch dependent beyond the initial mix. All subsequent steps are flow-through and occur under continuous conditions to allow high throughput with minimal variation. Formulation changes are implemented by adjusting source tank routing and modifying pump set points. Multiple product lines operate in parallel using shared infrastructure with staggered schedules and automated changeovers. Flavor switching involves purging lines with heated water, followed by air blows and conductance verification before the next product introduction. Nestle's frozen dessert output relies entirely on integration between thermodynamics, fluid mechanics, solids handling, and process control. Every movement and phase change contributes to the structural and sensory properties of the final packaged unit.